So welcome to this course on quantum networks within the Center for Quantum Networks Winter School. This course is titled Exploring and Designing Quantum Networks via Digital Twin Simulations. So this is the very first time that I am offering this course, and I'm super thrilled to be super thrilled to be joined by Prajit Dhara, uh, from University of Arizona, and also having worked a lot with us here at MIT, and by Dr. Hyeongrak Choi, who co-designed this brand new course with me for you today. The the big difference in this course compared to all courses that I have done on this topic before and that I've seen otherwise previously is that we've tried to make this material interactive by code. So rather than me just talking to you and a little bit of interaction, it will be a little bit of me talking to you and a lot of interaction, where together we will explore these topics of quantum networks from the physical layer, how to design quantum memories and interfaces to photons, through the protocol layer and application layers, all through simulations. And we call them digital twin simulations. So here, just a note on nomenclature. Digital twin is a term for something where we have a so-called anchored physical model. So, for example, if you had a twin, then your digital twin would be would match the measurements on you, right? Here, in this case, for quantum networks, when we talk about a digital twin of a quantum memory device, for example, then it is a physical model, but the parameters in the physical model are in agreement with the actual physical device. Okay, so that, for example, rather than doing an experiment perhaps on the physical device, you could then do an experiment virtually on the digital twin version of it. And the benefit there is that if you try to build a system that comprises of a multitude of subcomponents, such as a network, you can, if you have good physical models for the subcomponents, virtually assemble the system. And this is particularly important in the area of quantum networks where the subcomponents are still not mature, so that it's difficult to assemble a large a test bed in which you have some tens or hundreds of quantum repeater nodes, for example. We're doing that with a few, two or three, but so many of the properties of these kinds of networks emerge when you have larger networks. And so what we can do is create physical models that are pegged against our experimental devices, and then use these to construct bigger networks virtually to forecast where we should go and how to model and what you could do with networks that we anticipate in 5 to 10 years. So that's the digital twin part here. Yeah, this is the first time we're doing this. So I'll tell you in advance that some of the parts here you will see will probably not work so well. Some will work better. Would love your feedback. And we're excited to go through this first deployment with you. Now, another reason why we think this is the right time to actually create a course based on modeling, in particular in our case on Python modeling, is that even if you aren't super expert with Python code, recently enabled AI models, in particular large language models, make it possible to provide a tutor to everybody, where you can, along the way in this course, you can ask this tutor, and it should do a pretty good job of answering questions relating to the text, but especially also the code that you will be presented with in this class. And in particular, we are excited to trial here a new system that I just developed in my class for an MIT course, 62410, just this spring. And this is a large language model based on OpenAI's GPT-4 with retrieval augmented generation, RAG, that gives context to the AI based on the information that you're currently on. That is the web page that you're currently looking at, it knows. So it has context-aware information. And that, together with some other techniques, allowed us to get a very good answer rate, or a very low rate of false answers, hallucinations as they're called. They're sort of like confidently wrong answers. But that rate, we can't guarantee it to be zero. So do keep in mind that these are still developing. There's still like having AI systems that have a zero error rate is still a major research goal, not just for us, but really, for the biggest players in the field, Google, OpenAI, etc. But we'll see how it goes. So far, our experience is very good, I would say, on this system. So that's so back, I jokingly called that system when I introduced it to my class in the spring as a trial chat tutor, but that name has stuck. And fortunately, we've been joined by several hobbyist coders. Chuck is among them, but also special thanks to Adrian Areton and Alexandru Areton of the University of Polytechnica of Bucharest, and to Hunter Kemeny, who actually is a CQN alum. He was a CQN research intern with my group this past summer and got involved in this, contributed a great deal, and helped actually put Chat Tutor, this code base, into the form that it's in now, much better than I had created, and to put it online. So actually, it's now open source. So for people interested, you can go to this website here. I mean, go to github.com, Chat Tutor, and all the code that we're talking about that underpins this AI tutor is open source. Okay, I think this is the introduction now. Let me see, how many people do we have dialed in right now?
Currently, we have
How
53 people.
many?
Currently, we have 53 attendees in the
Okay,
room.
wonderful. Okay, wonderful. Unfortunately, I can't see who's dialed in. I would have asked like what your background is on. Okay, but again, there's a Q&A tool for us here. So the way it's going to work is we're going to have some slides, so give context, and then we'll go launch into code and we'll go back and forth. So sort of just to give some context, I think it's an exciting time to be in this field. We're really in the midst of a renaissance in computing. 10, 20 years ago, computing used to be about getting more transistors per unit area on a chip. Nowadays, there is a need for completely new computing paradigms, and among them is quantum information science, and lots of exciting advances there in quantum computing, for example, with microwave photons, with optical photons, with atoms, with defective atoms, ions, and so forth. There's also a parallel change in how we think about computing and how we use computing, and that is really from machine learning. Like deep neural networks are changing the way that we write code and are changing the way that we really interact with machines altogether. Both of these will be represented in this course. The first, in quantum information science, is the main topic, but we're using the second to help us understand the first. So when we look at building a quantum computer, for example, there is now, or there will be, depending on where in the development stage you are, a need to communicate quantum information from one set of qubits to another, and they may not be adjacent to one another, so that you need to somehow translate quantum information over a distance. This could be a modular quantum computer where like one sub area is connected to another locally in a data center, or it could be a distributed quantum computing system, which is really what we're talking about when we're talking about the quantum internet, a set of distributed quantum memories, which if we want to truly scale it, we'll have to have error correction on them. Thus, each node is really a quantum computer of its own and connected via links capable of transmitting quantum information. So whereas a quantum computer can be controlled by optical fields, semi-classic, which we can treat semi-classically, like for example, cold atoms or trapped ions or so as quantum memories interacting locally, but controlled by optical fields. This translation of quantum information from one location to another motivates the development of a network, where these links that you see here, these edges between our nodes, the nodes encode qubits. These links here are capable of transmitting quantum information by some means. There are sort of two primary ways of doing this. A, you, especially over long distances, you don't want to have to carry the stationary quantum memory over long distance. So you can couple the quantum memory here to an optical field, like an optical pulse, which then can race over to the other memory and couple to that memory. In this case, however, you're vulnerable. Your quantum information is vulnerable to coupling to the environment, to losses along the way. And if you care about that quantum information a lot, because perhaps it's sort of a mid-circuit quantum state in a quantum computer, then you might be in trouble in this case if this is a lossy channel. The other way to do this is to first establish some entangled state across stationary but distant quantum memories, and then to use that entanglement as a resource for teleporting quantum states from one location to another. So your qubits remain encoded locally in some long-lived memory, like an atomic state, but you can use local operations together with optical fields that have established some entanglement to transmit the quantum state from one location to another. And that not only applies to teleporting quantum states, but also even gates. You can interpret this as teleporting gates. So you can apply like a controlled NOT gate between distant memories in this teleported fashion. And so it's really, this is the quantum network that we're really primarily going to focus on. What I should say for the sake of completeness, that you could in principle also encode quantum information entirely in photons, not using atomic memories like electron and nuclear spins, etc. And for this, though, you need some sort of error correction on the to especially combat the losses that optical fields encounter. There's some directions towards that that are here in this representation on the right-hand side. One where you temporarily couple optical fields to matter. So this is sort of matter-assisted two-photon gates. If you can make these sufficiently good, you could create error-correcting codes. You have a universal set of gates, and with error-correcting codes, you could in fact store quantum information entirely in photons. And the other way is to not have inline nonlinearity as provided here by this matter-assisted scheme, but instead the nonlinearity that enable these logic gates derives from the measurement itself. And so this is called measurement-based gates. Here on the right-hand side, this is a technology pursued by a big company called Quantum, for example. Here is a technology pursued by other efforts, probably more in the superconducting space. Xanadu is another example of a company that's sort of in between here. But we're going to focus on quantum networks really here on the in this regime here. And I put this up because this shows you the spectrum of the encoding of quantum information, either entirely in fermions, in the electron and nuclear spins of atoms, or basically the the hyperfine structure of atoms, where the optical fields are just control systems, to here hybrid, where you encode quantum information both in optical fields as well as in fermionic systems, and here on the right-hand side, where the encoding is and the coupling is all in optical fields. In all of these schemes, there's a need to develop really by co-design algorithms, the control systems, and the fundamental, like the materials, the qubits, etc. And so you'll see that in this course, reflected in this course. Now, at this point, I want to just talk briefly about a couple of basic things. In particular, we have to make sure that we're all on the same page in what it actually means, what a photon actually means, right? So when you in a first year graduate class in quantum optics, you would begin by seeing how actually the optical fields are actually derived, how the quantization of that is actually motivated. And I'm going through this briefly mostly as an example here. So let's begin by considering a optical cavity made up of two mirrors separated by a distance L here, as shown here. We have our coordinate system here, okay? And so this is very simplified. We're assuming that these mirrors are infinitely large in comparison to the wavelength of the optical fields in between. And then that the mirrors are metallic, that they're made of conductors. As a result, the boundary conditions on the optical field here are that the electric fields at the locations of the mirrors vanish. Then we can write out our electric field, which of course is a vector represented here over space and time. And we can write this as a Fourier series over components that capture the spatial information of the field as well as the temporal information of the field, summed here over the eigenbasis of that problem with the subscript j here. So the C sub j here is the amplitude of the jth mode, where the jth mode is described by a temporal and a spatial component. And we're assuming here that we can separate these neatly, okay? Separation of variables. So if you demand that these eigenbases here are normalized, that is the absolute value squared integrated over the volume is equal to 1, then you get this prefactor here that encompasses a volume in the bottom here, namely given by the area, the cross-sectional area of the mode times the length. And so that's the electric field. We've imposed here the boundary condition, which then requires that which is satisfied if the spatial extent goes as sine of k sub j z, where k is some integer multiple of 2 pi over L. And once you have the electric field in this vector form, you can derive, since there are no sources, you can apply the Maxwell's equations, curl, etc., to find also the magnetic field. So you have electric field and the magnetic field. Having these, you can then ask, what is the energy in this electromagnetic field? And that, of course, is given by the energy density, given here by epsilon naught times E sub by the absolute value of E squared plus mu naught times the absolute value of the magnetic flux density squared, integrated over the volume, okay? And then if you write this out, you say, oh, wait, this actually is identical mathematically to the form that you'd have for a classical oscillator, right? For a classical oscillator, we have harmonic oscillator, we have a energy that's equal to k z squared, where z is, let's say, the extent of if you have a mass on a spring and you pull the spring away from its equilibrium position by a distance z, then there's a potential energy of 1/2 kz squared. Okay, and then in addition to that, of course, we have the kinetic energy, which is 1/2 for non-classical, for a non-relativistic system, 1/2 m z dot squared. Okay, this here is the total energy, H, for a harmonic oscillator. And if we plug in, and so this here, these terms here look like this, have the same mathematical form as the harmonic oscillator. And previously already in quantum mechanics, people quantized the system of a harmonic oscillator. And now in the late 1920s, they applied the same quantization rules then to the optical field, having noticed that they have the same math as a harmonic oscillator of a massive particle on a spring, for example. And then for that reason, people call this the second quantization, the first being the quantization of matter, and here is the quantization of optical fields. And in this case, it's useful to introduce these variables here. These are the conjugate variables that satisfy the Jacobi equations, where these are sort of the analogous terms for position and momentum, but in this case, they're related to the electric and the magnetic fields. And so written in these forms here, we can write the total Hamiltonian in this form, and this will be familiar to those of you guys who have already taken quantum mechanics. Here we have the energy of the harmonic oscillator is equal to its, again, here the kinetic energy and the potential energy summed. Okay, now writing this in the terms we just introduced gives us the quantization of the magnetic and the electric energy densities. And that's basically second quantization. Now it's useful at that point to introduce these other operators. So remember, in the first quantization of the position and momentum of a particle, we introduce the notion of operators in quantum mechanics, that all measurements are given by operators acting on some Hilbert space that describes the system. And here it's useful to introduce some additional operators, A and A dagger for the jth mode in this case, that correspond to the so-called lowering and raising operator of the energy of the harmonic oscillator. And these guys are represented here as sums and differences of the Q and P operators on that mode. And so if you just mathematically, if you just plug in these raising and lowering operators into our earlier expression of the quantum harmonic oscillator, and make use also of the commutation relations between momentum and position, which can be rewritten then in a commutation from which we can derive the commutation relation also for these raising and lowering operators as given here. This says that the raising and lowering operators, that they commute if mode I and J are different. I is not equal to J, but they don't commute for the same mode. Okay. And if we then plug this and this together into our earlier expression and simplify this guy, then we derive at this form of the Hamiltonian, which is going to be familiar to many of you. This here is the number of photons in mode J multiplied by the energy per photon, omega sub J of mode J, plus an offset, and this is the vacuum energy of mode J. Okay, so this is our total Hamiltonian. Okay, and from this, it's then possible, we're kind of going fast here, but this is really intended to be at the review, so we're all on the same page in sort of nomenclature. From this, one can then go back and plug in the previous equations, the Q and P back into the form of the electric and the magnetic fields, and then derive the operators that give the electric field and the magnetic field. So if you wanted to say, oh, what is the electric field? Okay, you need an operator for that. It's a measurement. So you need an operator in that Hilbert space, and here it is. So you can construct that operator out of your expression here for P and Q and this spatial extent. So just as an aside note, people ask, for example, like, what is the expectation of the electric field at a node of the optical field? And is there any fluctuation in it? The answer is there's no fluctuation in it, because the electric field at node where sine of k sub j times c is equal to 0, that electric field is 0, and hence the variance in electric field also goes to 0. However, the magnetic field there can be non-zero, and thus the variance in the magnetic field can be non-zero. Okay, so you can derive all this from these forms of the electric and magnetic field operators. Okay, next up is let's talk about how we can time evolve these electromagnetic fields. Here we make use of the Schrödinger equation. Once you have a state, you want to see how does it evolve it in time. Okay, you plug in your Hamiltonian, which we had on the previous page, and that, together with the Schrödinger equation, allows you then to find the time evolution of the state. If the Hamiltonian is time independent, which is what we're going to consider in most cases here, except for in quantum control, where we have like a control field, which would be a time dependent Hamiltonian. But if it's time independent, then you can solve this directly in a closed form, giving here this expression for the state evolution. Okay, so the state evolution is given by the deconstruction here of energy eigenstates denoted by J sub n, where J is the mode, so like the jth mode of the optical field. For example, like this here would be, if this is the electric field, okay, so this is the lowest energy state of the resonator. Okay, it has a node at this mirror and at this mirror. The next lowest energy state would be this one, etc. So this is indexed by J equals 1, J equals 2. And then each of these states has in and of itself some eigenstates in their energy occupation. For example, here, like a very weak field would be maybe like the electric field would be very weak for a coherent state, and stronger for a stronger field. So that coherent state would be constructed out of superpositions of these number states within one given mode. Okay, and we know that the evolution here, this thing scales as the energy of that state, which is E, the energy of the jth mode excited with n photons, divided by h bar omega. This thing is equal to that expression and times t, times I. Okay, so this is just e to the minus I, the energy of the state, divided by h bar times t. Okay, similarly, you can either evolve the state in the time domain, but in this picture, in the Schrödinger picture, or you can also evolve the operators and keep the states stationary, and that's the Heisenberg picture. Because this is a review, I'll skip over that here, but I just wanted to show it here because in our Python code, we're going to make use of both pictures later on in the course. Okay, so in review, a mode is a solution to the classical Maxwell's equations under the boundary condition. So absent charges, this mode would be a solution A here for this vector potential, for example. And from that, then that gives us the spatial distribution of the orthonormal set of solutions, the eigenstates of the Maxwell's equations. Where the quantum mechanics comes in is it tells us about the, it predicts for, it allows us to predict what the measurement of the excitation of these modes would be. So if you wanted to, for example, if you were to probe the electric field in this cavity, you would at strong, for strong fields, maybe you wouldn't notice quantum mechanics, but if they're very weak, you will notice a quantization in the electric field and its noise properties. And that is the quantization of the electromagnetic fields. And in order to describe that, you need to somehow quantize the excitations of that mode. And that's what we just talked about. And that then gives you the observables, for example, for the electromagnetic field in a cavity, E and H distributed in position and in time. Okay, and here's a simple example for us, would be this, but you can also construct out of a similar approach, you can construct traveling fields. For example, you have a TE, you could have a transverse electromagnetic mode, for example, the 0, 0 mode, right? In optics would be a field propagating in this direction, where the electric field is, for example, in this plane. This is the E field. And then the magnetic field, it turns out, is transverse when propagating through free space. And that allows you to build up the electromagnetic field of a traveling mode. And then if, again, you wanted to then say, what is the electric field at a given time or something like this, you should use quantum mechanics to answer that. And then again, you will arrive at some wave packet, which will look similar to what we derived here for the standing waves in a Fabry-Perot cavity. An important point here, I'd like to point out an important thing here that we'll come back to later, which is that the normalization terms here, this is the term that we had for normalizing our electromagnetic fields integrated in space. These terms here have that volume in the denominator, where again, the volume is the area of the electromagnetic mode A times the length of the cavity L. Okay, so we see here that the prefactor of this operator for the electric field, that prefactor depends on 1 over the square root of the mode volume. So if you want to get with a single excitation of the optical field, a strong interaction, so a single photon, a strong interaction with an atomic system via the dipole force, then you should make volumes small, because that will cause the vacuum electric field factor here to be large. And so that's an important lesson for doing cavity QED, which we will use for making efficient spin photon interfaces, where we really want to control the interaction of an optical field at the single photon level with matter at the single electron level. That allows us to mediate that quantum information from the internal state of an atom to the electromagnetic field connecting some number of memories, for example. Okay, and so once you have quantized the electromagnetic field, as we just did, for a single mode, then you can construct more complex scenarios. For example, here is a set of N modes, which maybe would be the N, maybe single mode waveguides on a photonic integrated circuits, or just abstractly speaking, a N mode system of any electromagnetic modes that you found by finding the eigenstates of a resonator, for example. And then you can quantize each of these independently, and you can construct wave packets out of it and describe complex electromagnetic fields, whether they consist of like photonic circuits with lots of waveguides on it, or if it's like free space propagation. You can use linear algebra together with the rules of quantum mechanics to construct these electromagnetic fields. Sometimes you will encounter not pure states like we've discussed thus far, but mixed states. And here the thing about the mixed state is that you have, for example, a photon which has some probability of being in any given mode out of this set of n modes. But suppose that the photon also had some component in an environment outside that mode basis. And the environment, which maybe we're not privy to, but nonetheless, it's coupled to the environment, causes some decoherence of the state, some or lack of purity of the state. And if you want to describe those kinds of states, you can do that by finding the density matrix, which essentially what it means is you write the pure state over both the system here of your investigation, like the system of your chip, plus the environment, okay? And then you trace out the environment, and that leaves you with a mixed state. Okay, so we'll look at mixed states, and these things have to basically take into account the sort of the probability amplitudes are modified, and that is represented by writing the density matrix. So rather than writing n amplitudes, complex numbers for the state with n modes, you have to write as many as n squared times 2 real numbers to represent the complex entries in the density matrix, minus the sum minus 1 because of the constraint of the basically the unitarity constraint. Okay. So once you have that, you can also say, okay, what if my time evolution is not independent in time, but suppose there's actually maybe some coupling between modes. You can represent that coupling by a time-dependent Hamiltonian. You can, oftentimes it's useful to sort of compile these couplings into discrete operations, discrete mode couplings. And that is represented here as for example, the coupling matrix between two optical fields racing down in one direction only, a two waveguide circuit, and passing through a integrated interferometer. And that allows, and here is the rules for how to couple the modes that emerge from that interferometer. So yeah, that's basically the background to how we can understand experiments like this experiment here. That's a major result that from the group of Zhenwei Pan in China showed a very large scale photonic integrated, very large scale multimodal quantum optics experiment made up of large numbers of signal mode squeezers that pass through some coupling matrix that are represented here physically in some interferometric apparatus, and then finally sampled onto single photon resolving detectors. And similar descriptions together with the cavity QED picture are what allows you to analyze, for example, the quantum supremacy argument in the center circuit sampling experiment by Google some years ago. Okay, so really that's the sort of like what we've talked about thus far is sort of is the basis for being able to really understand the core of the really present state of the art in quantum information experiments. But if you, for sampling experiments, but if you want to go beyond that and actually understand how to build error tolerant systems, there's additional like algorithmic work that has to be added to this discussion here of quantum optics. So you have to bring the physics and the algorithms together. And we'll look at some examples of that later on in the course. For example, Chuck will talk about how to compose algorithms out of sub-blocks here, especially in the context of quantum networks. Okay, so with this, I want to get into the code. So now we're going to take a look at our code base. So we posted it at the beginning of the lecture notes. Oh, actually, now that there's some additional people here, I want to just go ahead and share my slides with you all. Okay, there they are. And if you open them, you can click on this link. And that link actually was also shared earlier in the class. So this should bring you here. And so what you're seeing here is our Jupyter notebook for this class. And so if you want to, when you actually want to run code, you can, this is HTML. So if you want to actually execute code, you can do this two ways. You can see here. So you will be able to click on the rocket, and there's either a binder version or a Colab version, whichever is your preference for running the code. Okay, so now I want to just like take a moment to look at the introductory material. And here you see how to set up your code base running notebooks for QRub, which Chuck is going to talk about later. And let's just go through and look at an example. So here, right, okay, so this is down here. So let's take a look here at Introduction to Qtip. This is actually not content that we created, but content that we repo cloned from Johansson, who maintains the Qtip code base. So Qtip is a Python package developed specifically for for running quantum mechanics experiments or simulations. And we in particular will use it for our example code later on in this course. So if you know Python, this is basically an extension of Python. And if you don't know Python, you'll be able to ask this chat tutor right here at the lower right-hand side for help. Actually, I want to make sure that, yeah, okay, you can all see the right. Yeah, we're seeing the right page. Very good. Okay. Okay. So so I'm gonna open this up here in okay, so here you have your code. This is what you should be able to see on your side. And you can check yourself through some of these steps. So for example, what if you want to create a quantum state? Here, to do that, you can create an object, and they can call it in Qtip, they call it a quantum object using the quantum object class. Okay, so the object is a quantum object, which in this case has which has two states, which are labeled as state 1 and state 0. Okay, we can ask what is the dimension of this object, which would, for example, be dimension 2, and so forth. And then, like, we'll see this more in examples later, but so then you can use this quantum object for calculating, for example, for first, you can create an object to store the operators in our SU2 algebra that describe a qubit, and all rotations there can be described by 3 operators. These are known as the Pauli operators that rotate about the y, the z, and the x axes. So these are the sigma y, sigma x, and sigma z operators. And I think so. I'll just leave this for you. This here has examples of how to go through operators. Here's the harmonic oscillator, setting that up, and so on. But rather than going through these examples, but rather than going through these definitions, I think it's actually nice to just like use this as a reference and to launch into actually some interactive examples that are more exciting. So for this, we'll go to here. So if you can click on in the Python lecture notes, click on under introduction. There's a section called quantum mechanics and coding of quantum information. And let's open that up. Again, you can open it up in whatever your preference is. from Google Chrome browser. Colab works well. I don't know how well it works for another browser, but you could also use the Binder version. Okay, so here we are, quantum mechanics and encoding information. So here's some examples. Okay, so like how, for example, like one would be, the question would be like, how well can you see in the dark, and how does like GPS work? And these are the things that we will explore in this segment. And we're going to do it by Qtip. Okay, so here what's happening here is we're doing pip install. So we're installing Qtip. I'm piping this to null, actually a better version, but I should have done pipe install -q would be another way to write this so that it doesn't, so that it quiets the output. And then we're also installing the library here, and then from NumPy, which is the numerics package from Python, we're getting cosine, sine, pi, etc. Okay, so now we can look at, we just talked about traveling electromagnetic waves. So in the notes, we were just talking about electromagnetic fields, which we now, okay, so you saw how we can quantize the electromagnetic fields and how we can use the position of these basis states to create wave packets. And we can create one wave packet, for example, that would be a traveling wave. That would be a traveling electromagnetic wave. Okay, and so we could describe that by the operators that we had a moment ago. Now here we have a choice. We can there's a mode set that is there are solutions to Max's equations if you have a propagating wave from the left to the right-hand side along the z-axis here, where the electric field is polarized across in the x hat orientation or in the y hat orientation. And so an electromagnetic field, the electromagnetic field component here, we could call this maybe the vertically polarized electromagnetic field. This refers to the electric field component. And the other mode is the horizontally polarized electromagnetic field. Okay, so or we can write it here in this way, where this coefficient gives you the electric field in the x hat direction, and this gives you the electric field in the y hat direction. Now, once you quantize this, you can create an excitation of, let's say, the x hat polarized mode, or the y hat polarized mode, with a single photon that's exciting it. Okay, so here, for example, then we can create this state. Now, this state is a qubit. Why? Because here what we have is the qubit is a system in which you have two levels, and the first level here is there's one excitation in the H, let's say the H being this polarization, and zero excitations of the electromagnetic field in the V direction, and vice versa. Okay, so there's two states here, and in this computational subspace of either this state or this state, which have amplitudes of alpha and beta respectively, you have encoded a quantum bit or a qubit. So what's unusual about that, of course, is that whereas a classical bit is either 0 or 1, this can be in a logical 0, or it can be in a logical 1, or it can be in a superposition of the two, as representable by these amplitudes here, alpha and beta. Okay, so now let's actually see. Of course, like we also have to say that the state here has to be normalized. That is, the probability density integrated over all of the possible measurement outcomes has to be equal to 1. So here's a question that we can check our understanding against. Suppose that given the constraints imposed by this normalization condition of the state, how many degrees of freedom remain in alpha and beta to describe an arbitrary state psi? Okay, so the state these are complex numbers. So each complex number is represented by 2 degrees of freedom, the real and the imaginary component. That would be a total of 4 degrees of freedom for alpha and beta, but there's a constraint, namely that the absolute value of alpha squared plus beta squared has to be equal to 1 to make sure that the probability integrates to 1, and that leaves us with 3 degrees of freedom. Okay, so there's 3 degrees of freedom, but oftentimes people represent a qubit as a sort of a point on block sphere, and you can do that provided you don't care about the global phase. And so here we can see that in this animation, which you should now have access to. So here's a qubit, and neglecting the global phase of the relative phase between alpha and beta, which we can factor out as a global phase. So neglecting that, there's 2 degrees of freedom remaining, and we could call these 2 degrees of freedom theta and phi. Okay, and so here is how we could visualize the state of a qubit as a point on a unit sphere, block sphere, where the north pole is the state H, the logical state H, where you might call state 0, and then the south pole is the logical state V, or the state 1. Okay, now, so that's a qubit. Now, what is you'd say, well, another question, remember, what is the energy of the state? And so here we have just exercises that I think I will leave for you to explore these yourself. But I want to focus here on the logical encoding. So let's use our model to encode a qubit that is a physical state when measured yields one of 2 possible measurement outcomes, a 2-level system. And let's define a set of orthonormal logical states, 0 in the logical basis and 1 in the logical basis, in terms of these H and V polarizations. Okay. So a question here might be, what would be a suitable measurement apparatus for the two? How do you distinguish? How do you measure whether what fraction of a state is in H or in 0 or V? So, like, for example, I gave you the state psi, and this state is some superposition of 0 plus 1, where the amplitudes are given by alpha and beta, where again, you have the normalization requirement that alpha squared plus beta squared has to sum to 1 in the absolute value. And how could you measure what the probability of measuring state 0 of this qubit is? Okay, so let's encode the qubit whose logical states are given here. Let's encode that in a physical system as the horizontally polarized mode and the vertically polarized mode with okay, yeah, a vertically polarized mode, which has each of which is either occupied by 0 or 1 photons. But the total number of photons is equal to 1, the constraint. Okay, so then the way that you could measure this, what the amplitudes are, is for example, you could put the optical field through a polarizing beam splitter, and with the photodetector, measure the photocurrent, and that photocurrent is proportional to alpha squared for one detector and beta squared for the other. So that's how you could measure the state of the qubits of a set of copies of the state. And that's basically the measurement postulate, that every time you measure, you will either measure 0 or 1. You can't measure you can't measure any sort of number in between the two. Okay, and that's the point of this exercise that we've given to you here. Okay, now and then again here, actually, when you look at these exercises here with the chat tutor, if you have like if something in the code here is unclear, we hope that this will serve as a really useful tool. So like, let's just try it out. This is the first time we'll try it out I don't know, what should we ask? Is there, yeah, so Chuck, what should we ask here? Chat tutor. Okay, explain, you could say, for example, explain this to me. Let's see if it gets it right. So we're asking it, what if we considered instead of the optical photons, what if we considered microwave photons? So it says for the energy, it says that the thermal occupation of an electromagnetic field is so and so. Okay, to find the thermal occupation of an electromagnetic mode at microwave frequency of 3 gigahertz, we would calculate the photon energy and then use the Bose-Einstein distribution to determine the average number, okay? And the Bose-Einstein distribution is given here. So you see the code is still, there's an issue with our code in this first deployment. This should have rendered in Markdown. It didn't, but hopefully this is clear enough. You can use that relation. So we can follow up like solve, give me the answer for like room temperature. Let's see if it gives you the answer. Okay, now what you're seeing here is what we call chat tutor mode. So you can go to GPT-4 and ask the same thing. You can copy the content of our course and then put it into OpenAI and it will give you the answer. But we don't want people to do that. We want you, although I just told you how to do it if you wanted to. But we want you here that you really have an interaction with and sort of like learn by doing, right? So first, can you recall the relationship between the energy of the photon and its angular frequency? Okay, so E equals to omega times h bar, right? Okay, so now it's asking, given that the frequency is 3 gigahertz, can we calculate the angular frequency of omega? Okay, well, it would be 3 gigahertz times 2 pi, which would be about 20 times 10 to the 9 radians per second. Okay, it's being very careful there. It's right. That's roughly what we had estimated. Okay, so I think I'll move back to the main course, but here you see these are the resources that you can use to actually work through examples that we provide you with here. So far we've looked at just encoding optical fields in two-level systems consisting of a single photon in the H and no photon in the V, or vice versa, as logical 0 and 1 encoding. But you can use other basis states. For example, you could use as a logical computational basis, you could use the horizontal and the vertical polarization of the optical the left-hand and right-hand circularly polarized modes as equally good basis states for the logical qubit encoding. Okay, and there's exercises provided here that we would encourage you all to go through. We don't have time to do that here, but we hope that like with the resources given and chat tutor hopefully can help go through these exercises on sort of the background needed for the subsequent parts of the course. Now, I want to just talk a bit about how we can physically realize the encoding in practice. So far, we've just looked at examples of an optical field, in vacuum and so forth. That's not really realistic. Like if we want to build practical devices, we have to engineer the physics. And so I'll give you some examples of how you can do that. So one really useful tool that's come about in the last few decades is optical waveguides, high confinement optical waveguides consisting, for example, of a silicon guiding layer surrounded by silicon dioxide low index cladding. So then by total internal reflection, an optical field can be confined in a wire defined out of etching a silicon waveguide, and you can see as illustrated here. And that device you should, if you make it small enough, it can only support the fundamental mode. So that's what we will call a single mode waveguide. So that's a good way of preserving the spatial mode of an encoded qubit. Then of course you have to worry about like what are the absorption losses, scattering losses, etc., of these kinds of waveguides, and how would you describe these? The answer is, if you, for example, have an incident field here, which again we can describe by this operator of our electric field and so on, and you want to know what is the outgoing field here, you can describe the propagation through the waveguide as an optical channel where losses are modeled by partial coupling to an environment of optical modes. Okay, so for example, scattering is just you can model scattering as a partial beam splitter, scattering some intensity fraction eta squared into this set of other optical modes where the power, the intensity of the propagated field forward then would be square root would be 1 minus eta squared. Okay, so basically, if you want to model the losses in a waveguide, you can consider them as lots of little beam splitters, partial reflectors that couple your field to the environment. Okay, and this one we've already covered before. Okay, but so this is a way we can describe mode propagation in a photonic circuit, and you have different kinds of materials that besides silicon that are used. But silicon is a particularly mature technology to the point that actually increasingly telecom equipment, which runs your internet traffic, can be actually encoded and decoded by silicon waveguide devices. And here's an example of one of these devices. Here's your optical fiber entering through a grating coupler into a photonic circuit, which is located here. And here's an ASIC on top that does some of the control electronics for encoding and decoding, for like modulators for encoding, and transimpedance amplifiers for decoding steps of this so-called transceiver. Okay. Luckily, like this is developing this stuff can be quite expensive, but fortunately, telecommunications pays for much of that, and we in quantum can sort of bootstrap on top of that. There's some of the work that we saw earlier used random walks in optical circuits in bulk. There's interest to do also that in a more controlled way in programmable optics on a chip. And so, for example, my group has been working on programmable optical circuits of the kind that you can see here, where all of that stuff here in between can be represented as a unitary matrix acting on some set of input states in the linear optics regime. And so you can use the math that we've been talking about for the first part of this course. You can apply that to not just 2x2 couplers like a Mach-Zehnder, but really to large optical systems as demonstrated here. So here you can see some examples of the actual engineering, the packaging, the phase modulation, and so on that has to go on in order to encode quantum states into a superposition of modes and then propagate these through some programmable circuit. This, for example, here we have a total of 10 modes, which can be excited by some number of photons, and this gives you some examples of how to do these kinds of quantum random walks or boson sampling experiments using the toolkit provided to us by silicon integrated optics. Okay, so another part of that toolkit is to make use of the nonlinear properties of optical materials, and there in particular in silicon you have full wave mixing. So silicon, because of its symmetry, uh, doesn't have a second order nonlinearity, but has a third order nonlinearity, which gives you a Kerr effect, and that couples a total of 4 fields. Now, if one of the fields here is excited by 2 pump photons, for example, then this Hamiltonian here that shows you how the fields couple nonlinearly, proportional with the coefficient of the material, the chi3 coefficient of the material. These 2 photons at a pump frequency can couple to signal and idler photons as a way of producing spontaneous full-wave mixing. And so this spontaneous full-wave mixing, you'll see later in Prajit's portion of the course, we will use that to produce entangled photon pairs together with photodetection in a heralded fashion, and we will use that for midpoint single photon source based midpoint entangled photon source based entanglement distribution. Now, so I think I'll skip over the remainder of this part. And so at this point, I think I will, so Prajit and Chuck, are you guys ready to start with your sections?
Yes, I can take over the second part of the.
Okay, so I'm just about to pass it off to you. So let me just sort of introduce the next step here. So now that we have sort of the core of the toolkit, we see how we have like create photonic devices to guide light, to generate entangled photon pairs, perhaps using the Kerr nonlinearity, and so forth. Let's see how we can put different pieces of this technology together to make a system that actually does what we want it to do, like distributing entanglement over long distance, so we can teleport a state from one place to another. Again, like what we were at in the beginning, this sort of in the quantum network of a set of connected memories connected by optical fields that we can connect qubits at distance or realize gates at a distance. And so really the problem is, how do I compile an application that I'm trying to do onto the physical hardware? And you can initially, people were doing this a lot in a sort of an ad hoc fashion, looking at sort of like instances of problems. But if you have done a problem many times before, then it often becomes sort of repetitive, and you say, oh wait, I wish there was some sort of systematic way that I could encode the problem and solve it out of components. And that really is sort of summarized in the last 20 plus, I guess, 25 years or so of quantum network development, maybe even more, starting with Mabuchi's work, where a lot of protocols were developed. As sort of a zoo of protocols can be quite confusing. And in this work here with Chuck and with our collaborators, Hansen and Beauregard and Hans Borkers at Delft University, we tried to sort of tame that zoo of protocols by making it composable. And that is how we're gonna, and with this, I'd like to pass it to Dr. Choi, who will tell you about a really exciting step into making composable quantum network protocols out of Python with QTIP, which we've talked about thus far, but in particular, building into that framework this quantum remote entanglement building block simulation based on QREP. So Chuck, please take it, and you could go ahead and screen share on your side.
Yeah, thanks, Dirk. Thanks for the nice introduction. I hope my screen sharing is good.
Yep, we can see it. Mm-hmm.
Yeah, I'm happy to proceed right now, but like for audience, like should we have like 5 or 10-minute intermission, like so that people can, combine the
If you have any questions up to here?
perhaps we can have a like 5 or 10-minute break.
Yeah, let's do it. Maybe just I think a few minutes, would say.
Yeah. Okay, sure.
So maybe bring us up to speed in the meantime while anybody feel free to ask. I think the way to ask is with you can just I think the chat was disabled, what you were told.
Yeah,
But
there is a Q&A part on the like the lower menu bar. So if anyone has a question, like you can feel free to make a
oh, okay, so
question.
people have been asking already. Yeah, okay, great.
And you can also make the question as like anonymously. So yeah, please feel free. Dirk, we have like one question. Do you want me to? Can you see the question, or do you want me to?
Which one is? Yeah, please.
Yeah, the first question is, where can we learn about the foundations of what he discussed? How can we strengthen our background on the topics?
Oh, I see. Right. Yeah. So in the lecture notes, okay, 1 second. Actually, one second. So basically, in the lecture notes at the end, I have put a bibliography. That's a good way to learn about the foundations. And for studying such SOI-based quantum computing schemes, is electromagnetic simulation and quantum simulation required? Yeah, so you want to be able to simulate the quantum mechanics, and you can do that using the QREP package and the QTIP packages shared with you here. That's for the quantum simulation part. The electromagnetic simulation is not done by the code that we provide, but you can do that separately using eigensolvers, like for example, COMSOL or so, or finite difference time domain solutions like Lumerical. And I'll hand it back to Chuck.
Yep. Cool. Thanks, Dirk. Thanks for the nice introduction. Yeah, I'm Hyeongrak Chuck Choi. Please call me Chuck if you need to. I know my name is like probably a little bit hard to pronunciate it. I'm a postdoc in Dirk Englund group at MIT. I also did the PhD in the same group. I have been now working on the remote entanglement protocols for scalable quantum network implementation. And in this winter school section, we want to introduce the work so-called QREP, which is the abbreviation of the quantum remote entanglement building block simulations. And there are several reasons like why we developed this framework. This is a framework and like supported by the software package as well as a theoretical description of different protocols. This is the framework. So like we gave examples of entanglement protocols. We gave a toolbox for implementing the things, but a large part of the codes are actually open for community contribution. So yeah, please feel free to use it. Like you can also make your own repository and put the merge request so that we can develop this nice framework all together for making quantum network scalable. So let me briefly introduce what is the QREP. As Dirk explained, like if you open up, like if you search for different remote entanglement protocol, which is the essence of the quantum network. Basically, quantum network is like connecting different quantum modality with photons, because like it can be other than photon, for example, like microwave photons or something else. But as of right now, like we don't have a good medium for transmitting quantum information other than photons. So let's keep the focus on the photons. With the optical fiber, we can transmit the quantum information pretty well. Like these photons will transfer quantum information to connect different quantum systems by the form of entanglements, which is the quantum element that are not existing in classical physics. So, however, and there can be many ways of creating the entanglements. If you're actually like searching for the literature, there are many different protocols with different advantages and disadvantages. And as we always do in research, like we are always claiming the novelty of the method, like the strength of the method, but it is really hard to actually compare different methods. For example, in the group, I'm working on color synergy in diamond. If I want to work with very specific systems, say I have a color synergy, like silicon vacancy synergy in diamond with the optical waveguide, I don't know which protocol I should use. Like I might need to study different protocols, but studying different protocols will take the whole PhD years. So the reason why we made this framework is systematically first of all understand different protocol in a systematic way, so that at different level of understanding we can still understand all the protocols in an abstracted way, as well as we can compare it quantitatively to find the best protocol tuned for your own systems that you want to use. So that's the thing. And what we focused on is the level of abstraction. So this is why we call this framework as a building block framework, because when I started my PhD, in the first year, I know probably quantum circuits, basic quantum circuits, like the CNOT gate, plus states, zero states. But I don't know well about what is the second quantization, for example, that Dirk explained, or what is the cavity QED, etc. So but still I want to know about the remote interaction protocol. So and I want to design it if possible, without worrying about cavity QED or light matter interaction. So if that's the case, we can actually work on the remote entanglement protocol only at the very abstracted high level way, as the classical information processing does. Like when we are coding the Python, we don't worry about how the transistor works, right? So we actually made this layered architecture, which is basically giving a different level of understanding in this framework. We also, I'm gonna talk about the detail about this framework with each layer individually well. But before going on, I will give a brief overview about our framework. We also made this software package to support this framework, which is open sourced in the GitHub repository. You can actually find the repository link here. Or you can just search for QRep GitHub on the Google, and we put the installation here. We made a pip environment, so you don't have to worry about all the dependencies or contradiction between the packages, but you need to just run some of the packages. Then I'm gonna talk about the detail of our packages from the upper layer to the down layer. Probably I'm gonna give a full overview about this framework. But if you have your own interest at some point, you can probably stop and you can go over this course material in more detail to understand the degree, the operation of quantum network at the degree that you want. I also want to emphasize that our work has a manuscript that's on the archive. So if you click the link, you can actually find the manuscript that actually describes our protocol in a more complete way. We also made this lecture note, like in an interactive way. Again, like there are codes. We also have an example notebook that I'm gonna go through, like to actually for you to actually try this framework by yourself. And yeah, like during this like presentation, I'm gonna go through it like only in a very brief way because of the time limitation. But if you have some time and if you're interested in our framework, please go through this lecture note, because like we like made this lecture note in a way that like to learn our framework in the easiest way. So let me start. Yeah, like I gave a brief overview about our framework. Then I want to explain like what is the photon-mediated remote entanglement protocol. As I said, until now, as far as we know, the best like way of like transmitting quantum information is a photon, because like if you have a spins, like it's great that like we have a long time quantum memory, but they decohere or they can be relaxed, so that like we cannot maintain the quantum information in a long distance. While the photon, like it has a basically infinite thermalization time. The only limitation is that it's very hard to store the photon. But if you are actually transmitting the quantum information in a long distance, optical fiber is a great material, because like every quantum information can pass through speed of the light, so we can actually do very fast like quantum communication or like generating the entanglement. So yeah, like typical way of generating entanglement is we first make the photon or photonic field interacting with the spin that Alice has, or like the one of the party has. We typically use the Alice and Bob in a network setting as a two-party of the communication. Alice make the interaction between her spin and the photon, send the photon to the Bob. Bob makes the interaction between the photon and the spin. Bob either detect the photon or absorb the photon into the spin to make the entanglements. So this is a typical way of like generating the entanglements. And as you can see, it is fairly easy for the spin and the photon, and most of the most of the physics for generating entanglement is at the interaction between the spin and the photon. And there can be many different like way of like using the spin photon interface, basically making the interaction between the spin and the photon, which will allow like different entanglement protocols. So here I'm gonna go through our framework. This figure basically explains the layered architecture of the framework. First, when we have this entanglement protocol, we can consider different geometry or the topology of the entanglements. For example, like we can make the spin photon interface at Alice and Bob individually, saying that like Alice make the interaction with her spin and the photon. Bob does the same thing. We collect the photon in the middle, like we often call the Charlie. Charlie collect the photon, make a like mode mixing between these photons, then detect the photon to make the entanglement between the Alice and Bob. For example, like if Alice send the photon and the Bob send the photon, Charlie detects the one photon. But if Charlie detects only one photon, then we don't know. Alice doesn't know. Bob doesn't know. Charlie doesn't know. Nobody knows whether the photon is coming from the Alice or Bob. That means that the spins of the Alice and Bob, nobody knows like the states of their spins are in some direction. So we can make the quantum superposition between the two states, which will create the entanglements. I'm going to go detail like for later. But let's like first see how the topology works. In the other way, we can generate the entanglement in a linear way, as you can see in the middle panel here. You can first make the single photon interacting with the Alice's spin and send it to the Bob to make the interaction, then detect it. The other way is, say, like we generate the entangled photon pair in the middle by the SPDC. These photons are entangled. These are interacting with the Alice and Bob, like, individually. Then if we detect these photons, the photonic information is transferred to the spins so that like we can entangle the spins. And there can be even like, more geometries, like, like different geometries, but these three covers most of the entanglement protocols that are out there. So like we showed only three, but you can probably come up with, a new protocol with our method. If you're focusing on the center one, like the linear geometry, where the photon is sent from the Alice to the Bob, we can actually, this is like only very brief introduction. So we need to use which basis of the photon that we are going to use. So the next layer, next lower layer is encoding layer. We need to choose which spin basis that we are going to use, and we need to choose which photonic basis that we are going to use as the photon basis. For example, in this figure, like we choose the early and late time bin, then like saying that like we just randomly choose the early and late time bin, or like we made an educated guess that early and late time bin encoding is having some advantage. Then as you will see later, like we give an autonomous way of generating the detailed components of the three photon interface to make this protocol working, basically. And in that way, so like we have a two photonic mode, like where the photon is passing through. We have this like spin photon interface block that, again, like we know how to do that. Like you can like study it if you want to know about it. You can do it like in an agnostic way if you're not worrying about it, to focus on the photonic encoding side of the entanglements. So we can do this encoding to make we can do a little bit more detailed level of description of our protocol if we focus on the encoding level. But also at the same time, if you want to go a little bit deeper, saying that, oh, I want to know like how I should operate the physical system, because say I'm experimentalist in the lab, then we need to know what is the detail, like what actual physical operation we need to do on the chosen basis. So like for example, like if you are doing the spin photon interface, which is like doing the interaction between the spin and the photon, we can choose like different way of like doing the interaction. For example, in the cavity QED, we can use the amplitude of the transmission coefficient, or we can use the phase of the transmission coefficient or reflection coefficient. So there can be multiple ways. We again give a autonomous way of like configuring like this higher level block into the lower level block. And again, like the same is working for this is not only for the spin photon interface. The same can work for the photo detection, like the photon side of the quantum system. We know how we have a way to autonomously figure out how to do the photonic part of the operation, or the spin part of the operation, like although it's not shown here. And lastly, like if, for example, like you are a quantum optics theorist, you want to probably know more than the idealized like quantum operations. For example, like you want to know like what, like based on like your physical parameters, say like, what is the cavity atom coupling rate, as Dirk derived in his like lecture note. Like what is the spontaneous emission rate, what is the Pauli factor of the cavity, then you can calculate everything numerically exactly with this level of understanding. And you can also incorporate like variety of like imperfections. For example, like the trace cell loss, the uh, the loss of the photon while propagating through the optical fiber, the loss of the spin photon interface by imperfect cavity operation. And again, like this full framework is supported by the Python package QREP. So we are going to go through like this example notebook later, like for to see how this like framework actually works. And this code is like exactly reflecting this framework. Like, like if you want to code like something at the logical building block level, you need to use the logical building block in the code. If you're actually using the encoding level, like you need to use the encoding level blocks. And like we hope like, things are, the community is like developing this framework so that like, people can use like, other people's like blog implementation for studying their own blog and like contributing back to the repository so that like, everyone can get the same understanding about the protocols. I also want to emphasize that like we are very interested in machine learning approach of the protocol designs, because again, like probably the one of the first entanglement protocol has been out there like more than 2 decades. Like it's like like at the end of like 1999, 1998, like people first like come up with like this remote entanglement protocols of the 2-quantum memory. Like every month, like there is a new like entanglement protocols based on different protocols, different physical systems. All the people say like, this protocol is the best because like, A, B, and C. We think like, yes, like depending on the system, depending on, like the physical parameters, there is always the best protocols. It's just like, very hard for a PhD student study everything and like, calculate what is the best protocol for one setting. So we are very much interested in like, computer actually found the best way given your condition, for example, or given your specification, what is the, like the minimum, requirement specification for achieving actually your target application. Then like it is very important to make a modularized framework code basis for the machine to reconfigure and study the protocols. So the reason why we made like all the like we also call this as a building block or the Lego block, Lego block, so that the machine doesn't have to worry about inside of the block. As long as the user provided the blocks, the machine can like combine the Lego blocks in different way. And like sometimes like the machine can do in a very dumb way, but sometimes like they will find a new protocols like that will be better than other existing protocols. So that's our hope, and like stay tuned for our update. But for now, like let me go through like how we actually made this framework and how we configure this work. So for the QREP repository, like I guess like we are gonna have like the notebook going through sessions like at the end of like this presentation. So let me first explain how to actually install the QREP package into your local machine. You can do in many ways, like again, like as the previous session, you can also do the Google Colab or Binder, or you can do it in different way. You can just download like your IPython notebook or stuff. But if you actually want to do everything on your local machine, you can do it in a very simple way. if you have a Git on your machine, then you can just clone your repository through the Git. You need to just type the Git clone and this address on your terminal. And if you don't have a Git, please go to this repository. I think it's not, yeah. Please go to this repository, and if you click the code, this is a GitHub repository, you can actually download all the codes onto your local machine, then you will have all the codes for the QRAP. We are using many like existing packages, like including the Qtip. We included all in the pip end, pip environment. So you by typing these commands in your terminal, if you have a pip, it will automatically configure all the dependencies of the code into your local machine. So then like you need to type a few commands like to actually configure the things, and then you can run your Jupyter Lab for implementing the code. And like again, like for making a nice ecosystem with this framework, we made extensive comments on the codes of like our QRAP. For example, like if I'm going to the library, one of the important packages actually named quantum object. We say NQOBJ. We made all the like instructions about like how to use like this code. We really like work hard like on explaining the code to the people. So please feel free to take a look at the the base code like in the leave folder, like for tuning it for your own purpose. For example, like if you're seeing the quantum optical modeling layer, like we made all the details about like the parameters. So let's go back to our framework. The first layer is the logical building block layer. And as I briefly said, like in this layer of the framework, we talk about the topology of the protocols. We can have like three different topologies, the representative, we can have like three representative topology for the remote entanglements. The first one is again like Alice and Bob generate the photon, and the two photon meet in the middle, like so it's called detection in midpoint protocol. The two photons meet at the middle, like we do the Bell state measurement to the entanglements. And again, like there are details of like how to implement different the protocols, but essentially all the protocols are same in the sense that they are basically using one computational basis of the photon with the CNOT gate. How to implement it, like we're gonna go through it later, but it's also given automatically. But basically, all the detection in midpoint protocols are corresponding to this quantum circuit, as long as like we are dealing with like this zero states and CNOT gates properly later for physical implementation. If you are doing the linear geometry, at least first make the interaction between the photon and her spin through the CNOT gate. Photon is going to the Bob, and then doing the CNOT gate, then detection in the G basis. All the protocols like that has a sender-receiver topology or the linear topology is corresponding to this category. If you are doing the sourcing midpoint entanglement protocols, it's basically generating the entanglement between two photons. With the basis changes, it's all same as the plus states, and the zero state photons are passing through the CNOT gate to get the Bell states, and they are making an interaction individually with the spins, and the photons are detected to transfer the entanglement to the spins. So these are the third kinds of the entanglement protocols, so-called source in the midpoint protocols. And the source in the midpoint protocols are not well, like, like there has been some proposal from the old times, but like, it has not been thoroughly studied in the community with, like my colleague, like Kevin Chen and Prajit here, who is going to give a third section of like this winter school session. We'll talk about like this sourcing midpoint entanglement protocol in more detail. Okay, so and in again, like we identify first the topology of the entanglement protocol in a logical way in the logical building block layer. We need to identify what spin photon interface block, like how to implement this CNAT gate with the spin photon interaction in this layer. So we actually put some of the like the representative like physical interaction here. One of the thing is the spin photon emission. So for example, like when the spin photon emission means that like when spin is in one state, say like I will make the spin down as a 0 state and the spin up as a 1 state, but it can be anything. It can be orbital states, or it can be like different, like, wave function of the quantum dot confined, like wave function of the quantum dot confined in the, energy potential. Any like two different states will give a different interaction with the photon that can give a spin photon emission. For example, like for color centers, like when you're at 0 states, you're not emitting the photon because your energy level is large. While like if you are in the 1 state, then they can emit the photon under the illumination of the laser. So in that case, depending on the spin state, which is the blue line, the photonic states can be changing. For example, like photon states can be 0 to 1 because like we are emitting 1 photon. If you are thinking about the Fock state basis. You can also have a spin photon gate. For example, photon is interacting with the spins, like to change the phase or the amplitude or something. That can implement the CNAT gate as well. Again, like at this layer, we are not specifying with like how to implement like this like logical gate in detail. So we are leaving it as like like as an abstracted way. But whenever like you're configuring your entanglement block, and if you need a CNAT gate, you can think of like either spin photon emission or the spin photon gate. And another popular popular way of implementing the CNAT gate is actually the spin photon projector, because like sometimes these spins are having a optical transition that are too similar, saying that their energy separation is about same, so that like we cannot deal with like this with like optical pipers. Then we need to use the spin photon projector, so-called. This is like literally same as a projection operator that we are using in the quantum mechanics, but this spin photon projector can be used to configure the CNAT gate in a very specific way. So if you're using the spin photon projector in a proper way for configuring the CNAT gate, it's always in this form. It's not exact because you can do it in different way. You can make you can use the spin photon projection in a different way, like to not make the CNAT gate, which is not useful for the quantum network. So that's why we have like this approximately same sign for these two blocks. We can also do the spin photon absorption. Absorption is not usually used in the quantum network because like oftentimes photon is lost. But if we detect the photon, we can make the entanglements. Then like we know like when the entanglement is generated. So we are not often using the absorption protocols because you're losing the information there. However, like for the completeness, like we put the absorption, in this block, like which can also implement the CNAT gate if we are allowing the measurement of the photons. So these are the logical building block, like spin photon interface of the logical building block. We can also make the photon blocks like with this logical building blocks. These are rather like, trivial. I'm not going to go through the details, but like, for example, if we have a single photon source, like we can basically we can think of it as like the initialized states of the photon, which is like in a simple line. We can think about like photon pair source, which is like shown here. We can also do the detection in G basis or the Bell-Stein measurement by configuring the circuit in this way. Okay, and like lastly, spin blocks. I'm really like not gonna talk about the detail because like these are really like just the quantum gate. We like if you want to do the like the rotation around the n-axis by the angle of theta, this is the same as the like we are putting the gate in the spin line. And like like again like we made this framework to be open. Like you can implement any of like your logical building blocks into this framework. For example, like to implement the frequency conversion block for long distance communications or others. And given this like configuration of the CNAT, we can directly plug in this like configuration into the topology to get the logical building block layer compilation. So for example, like in the first protocol where the midpoint detection protocols, like we can replace the two CNAT gate by the spin photon emission block as shown here, or we can implement the sender receiver or linear topology with the spin photon gate here, or we can implement the midpoint detection, the source in the midpoint protocols with the spin photon projector as is shown here. So again, like this is kind of like autonomous, like when you choose your topology, when you choose like your spin photon, like which protocol you're gonna use, like either spin photon emission or spin photon gate or spin photon projector, you need to just replace that part with the block, logical building block. So after configuring our quantum circuit, we need to think about how to choose the basis of these quantum circuits. Because the quantum circuit assumes that like we have a computational basis, 0 and 1 states, but it doesn't determine like which is the 0 states and which is the 1 states. Like you need to define whether 0 states and 1 states is the polarization or frequency or different like implementation. And there are a few different way of like doing it. One of the way is like choosing the Fock state basis or number of state basis. If there is no photon, it's a 0 state. If there is a 1 photon, then it's a 1 state. Or we can choose the time bin basis. If the photon is in the early time bin, if photon is arriving, say, at 0 second, then it's 0 states. And if photon is arriving late, like saying that it arrives at 1 second, then it's a 1 state. We can make the qubit implementation in different time bin bases. We can also choose the polarization basis, whether your electric field is in horizontal direction, oscillating in horizontal direction, or vertically oscillating in vertical direction. Depending on it, like you can make it as a 0 states and 1 states. You can also choose like circular, like the clockwise rotation polarization as a 0 states and the anti-clockwise rotation as a 1 state. You can choose any of like polarization basis for your implementation. You can also choose the dual layer basis, like saying you have a 2 spatial mode, saying you have a 2 waveguide on the left and the right. Left, if the photon is on the left-hand side, like it's a 0 states, photon is on the right-hand side, there's 1 states. That's called as a dual rail basis that is often used in linear optic quantum computing because of the resilience under symmetric loss under the symmetric channel under the loss. And we can also choose the frequency basis for that. Other than that, like there can be many other like way of like encoding the photons. Like we choose this 5 because like these are the most like popular implementation in the community. But for example, like you can use like orbital angular momentum basis that are like often used in recent demonstration of like the high dimensional like cases. Or like you can even use like random basis like for protecting it from the highly like impulsive like noise. You can choose anything and like you can implement it and you can subsequently use it for your own entanglement protocols. And in all of like these kind of like basis choice, except the focus state basis, you can encode this like basis with the single photons or weak coherent states. For example, like they are approximately same when the weak coherent states has a low amplitude, but weak coherent states has a disadvantage that like they can have a 2 photon states or 3 photon states or even higher multi-photon state. However, if you actually use a very, very weak coherent states, this probability can be easily suppressed. But the problem is that then like you will have like significant portion of like your state to be 0. However, if you're choosing actually the post-selection type of like type of entanglement protocols, for example, like the heralded entanglement protocols, then because like you're only post-selecting the cases where the photon is detected as a one space, you can ignore this like overlap between the weak coherent states and the vacuum states. So in that case, you can use it. So there is a trade-off like between these two choices. We made the outline for the weak coherent states just to distinguish the single photon states in the diagram. There is obviously the trade-off, like the weak coherent states has advantage in the easy experimental realization, but other than that, it has all the disadvantages. However, like these days, like easy implementation is like really important. So like we want to give a full picture that whether you want to use a single photon states or the weak coherent states in your protocol. And after choosing your photon encoding, we need to implement this. We need to implement like all the physical operations that are working with this encoded block. So we need a physical building block, and like the spin can be also encoded in different way, but the photon is like most notable differences. So here is the table for the photon physical building blocks. For example, if you choose the Fock state basis, your measurement of the Fock state basis is just a single photon detector, meaning that like if you have a click in your photo detector, you detect in the 1 state. If you don't detect the click, then it's a 0 state. It's like idealized photon measurement operation. You can also have a mode mixing operation by just beam splitter. You can do the G rotation of the states by just having a wave plate, because like the 0 photon states does not experience the phase rotation, while the phase plate will give rotation on the single photon states. And likewise, like we made a complete table for all different, these like encoding bases to implement the quantum operation, like basically logical building block operations like the measurement or mode mixing or Z rotation or X rotations. Like for example, like so what you need again, like these are autonomous, like when you decide like your encoding. Hello?
Hey, Chuck, there are some questions maybe you could quickly look at. So one is, if I can just interrupt for 1 second here.
Yeah.
Okay, so one says, but we can use but can we use weak coherent states for entanglement, or are they mostly used for propagating and measuring QKD? Daria has answered. So Prajit is answering that. And the second, maybe we take this. So Prajit is answering this. The second question, this one coming from Ansh Singhal, is: can we encode multiple degrees of freedom into quantum states for realizing hyperentangled states, or simply monitoring the effect of operations on multiple degrees of freedom of the photon simultaneously?
Yeah. Let me first answer the second question while the project is like typing the answer, like if it's done before.
Yeah.
I will skip it. But thanks for the really nice question. I think this is important, like point. For realizing the hyperentangled states, yes, you can choose like multiple degree of freedom, not this like single degree of freedom to implement the thing. And like I mean, to be honest, like we haven't considered it like much. But I think it can be at the end, like even though things are hyper entangled, if we are working at the quantum circuit level, so we can encode it into the computational basis. So we will not have to worry about like the interference between the logical building block and the encoding layer. So what you need to do is like properly define your hyper entangled states into the computational basis. It probably can.
It's really just the size of the Hilbert space that matters, right? You could get that size of the Hilbert space either by one cavity mode that has, let's say, 10 possible Fock state occupations, or two modes that have 5 each.
Right.
No, that's not right. Something like this. I shouldn't have used 10. Should use powers of 2. But it's just the number of this dimension of the Hilbert space that matters for how much information you encode. Yeah. There's another question here. You want to look at the other one? It's actually quite useful too to look at.
Let me answer like one more thing. Here, like we mostly consider the qubit basis because the qubit basis are often preferable in the quantum network because of the easy implementation. But yeah, like definitely like higher dimensional like Hilbert space is like interesting to explore. And I want to invite Ansh like to actually use our package, implement like hyper entangled space if it's of your interest. And like like the push the merge, like that we will be happy to incorporate that like for the other people's use. So we are really inviting like people for the uses and the development of the framework. And Dirk, let's go to the second question. Second question is, could you please explain the main difference between this QREP quantum simulator and the NESPID quantum simulator? Yes. So NESPID is a great simulator for the network level simulation. It's often used for the link layer level of the simulation, saying that like we are given the coherence time, we are given the rate of the entanglement generation. It can be either probabilistic or deterministic. Then to study the network property of the quantum network, it is the perfect framework. However, it does not give an idea how to implement the entanglement protocol, which is like probably a little bit lower level description. Lower level meaning that like more related with the hardware and the physics level of the protocol. So we developed the QREP to kind of like explain this like physical level of like description, as well as like how to configure logically the entanglement protocol that can possibly give a result that can be fit into the NESPID too. Yeah. So I would say like there is a differences in the subject of the simulation. Yeah. I hope this answers the questions to the audience, but please feel free to give a additional question if you have. Yeah. Meanwhile, let me proceed with the photon physical building block. We also give a conversion of the photon encoding. For example, you can change your photon encoding in the midway for making an easier implementation. Then we offer these conversion blocks. And what we found is that as far as we know, most of the basis conversion needs a bypass through the dual layer basis. So if you want to convert, for example, time bin to the polarization, we need to convert it into the dual layer. Then we convert the dual layer to the polarization. But the things are pretty easy in the dual layer basis. So the conversion should be made through the dual rail for easy implementation, as long as we know. We also give an example of the Bell state measurement, this is mixing here. Bell state measurements needs a mode mixing and the detection measurement block. So you can configure your Bell state measurement by choosing the right mode mixing and the measurement depending on your basis choice, encoding choice. So lastly, in the physical building block, the most important part is actually spin-photon interface. Spin-photon interface can be also implemented in multiple different ways. For example, if it's a spin-photon emission, we can use the spontaneous emission of the spins, or we can use the elastic squaring of the photons, which will scatter the photon into the coherent states. We can also choose the Raman scattering, which is going to give a single photon space, but in a coherent waveform. If you're implementing the spin photon gate or spin photon projector, then we can, we can choose the conditional amplitude reflection. So, for example, depending on the atom space, our photon can be reflected or transmitted. Again, in here in diagram, if the spin is 0, then everything is transmitting. Even at the operation of our photon, if the spin is in the 1 state, the photon has a 0 transmission amplitude, meaning that it's all reflected. This is encoded in amplitude way, but we can also encode it in the phase way, because when the atom is inside the cavity and that alters the cavity photonic field, then you can change the phase. So for example, if atom is if the spin is in the up space, then the photon is reflected with the reverse phase. While if spin is in down, then it's reflected with the same phase. It can be also shown here and at the operation frequency of the photon. And I'm not gonna go through the detail, but we again have an automatic way to configure this spin photon interface that is correctly working for different encoding choice, as shown here. And we also linked some of the recent demonstrations of the remote entanglements with these configuration. They are all included in this framework by just spanning the combination of different choices. If we figure out this physical building block, we can basically simulate our network level of operation, how well it works and what is the the rate of entanglement generation and everything. But if you're interested in your physical hardware, you are designing, for example, photonic cavities, like how to make the interaction stronger by reducing the mode volume. But you don't know like how these like modification affects like your network performances, then you need to correctly model this physical system and include it in your simulation to get the deterministic result. And what you can like here, like we basically consider all the possible like noises and the coupling parameters of the spins with the cavities to explain these things. We also made all the modeling for different part of the physics. You can just like use it, but also at the same time, if you are quantum optics theorist, that you want to consider additional effect, because like we can always like our level of distraction always depends on the approximation. For example, like some of these like modeling assumes only the first order errors. If there is a second order error, if you want to identify what is the result like effect of like those errors, like you can include like those in your quantum channel description to actually see the effect of that. And again, like I'm inviting you guys like to actually use these protocols to study your own protocols. I think I saw one of the questions which seems to be answered. Yeah, so and like again, chat tutor is here, so please feel free to use the chat tutor for navigating navigating our framework in more detail, like, and if you have questions. And again, like I'm not gonna go through all the mathematical details because like this might not be the central message of like this framework. But if you want to go through like the details of the protocols, that we made a pretty detailed explanation on how we actually modeled these blocks with the references to the papers. So at the end, like by using this framework, we actually studied like different protocols like that are out there, and we actually compare different protocols in a systematic way, and like we can easily change these parameters in this framework. Is just like typing this one line of the code like to change all the parameters to actually simulate these different cases. For example, like again, like I'm not going to go through like why like the plot looks like this and like why there is like these shapes, but sometimes like sometimes like the operation of the remote entanglement protocol are not intuitive. For example, like if you're increasing your cooperativity of the cavity QED system, often people think that like your fidelity of the entanglements is like getting better, but it's not. Like for example, you can see multiple crossovers when you're sweeping actually your parameters given your choice of the protocols. You can also see that like like even though you're using the spin photon gate or spin photon emission, there is always like different regime of operation. So you might like, even though like you have a full ability to tune your cavity, design the cavity, you might want to actually not just like optimize everything, but choose the right parameters like to get the best entanglement fidelity, for example. So that is the part of like introducing the QRAP, and like we are gonna go through the notebook that's actually implementing our one of the protocols like called conditional amplitude reflection spin entanglements protocols. But before going on, if you have any questions, like please let me know. I will pause here like probably a few minutes, like in case like there is a questions. Yeah, then like proceed to the example notebooks. Okay, if there is no questions, I will proceed to the notebook. But feel free to give questions like in the meantime, like if you have any. So we first need, so after installing the QRAP on your machine, as you can see here, you can follow like this kind of like instructions. You can now use like your QRAP, and you can also like do it in the CoLab. Like then like we need to import the packages, like which is all again like included in the pip environment. We need to import the library functions like offered by the QRAP. Here I'm first like importing the logical building block. We abbreviate it as LBB. We import the physical building block, which is a PBB. We also import the named quantum object here. This is another feature that we introduced in the QRAP. This is enabling operation of the the operation of the quantum states with the naming. So we made a basically dictionary for the quantum object. So you don't have to remember your dimension of the quantum states for manipulating your quantum states. For example, like if you have two qubits, one qubit for Alice, one qubit for Bob, then you will have a 4x4, like 4x4, for example, like density matrices. If you're doing the operation on the Alice qubit, you need to remember that this like 4x4 matrix is actually not the 4x4 matrix, but the tensor product of the 2x2 matrices. So then like you need to operate you need to apply the operation for the first 2x2 matrix out of like this tensor product. You don't have to do it with the named quantum object that we implemented. You can type the Alice for your operation, then they will automatically configure where which part of the Hilbert space is actually for Alice and which Hilbert space is for the Bob, and they will automatically configure it. As well as this named quantum object offers the computational advantage when there is a vacuum states, saying that Alice and Bob detect the photon, the photonic states are remained as a vacuum, then they can automatically configure that this is the redundant states to get rid of it. Last thing that I want to emphasize is that if you're using the weak coherent states, then weak coherent state is technically infinite dimensional in the Hilbert space. So even though there is a very small amplitude probability amplitude in the high number of photon states, but this named quantum object is dealing with coherent states as coherent states, so that it can it does not waste your computational resource or doing the approximation to save the resource for doing the calculation with the coherent states. Then again, we need to import the encoding part of the code and the quantum optical modeling part of the code to actually do the operation. So first, we are going to look at the logical building block and encoding of these two that we went through in the note that we just saw. Then we start. There's some broken inline math, but basically the code can configure this out by defining our example protocol, for example, here. So first, we need to initialize our density matrix with the Alice states and the Bob states. We made projectors for no vacuum projector, meaning that we detect the photon, and if it's one photon or two photon, then it's all detected. We define it for the two, for early and late. Then we have a state up, for Alice and Bob states, state down, down for Bob, and these are the target states that we need to configure. So because this is a protocol, this is the part that you need to code by yourself for defining your protocols. But then, like, you can actually configure your logical building blocks by using the function of the do LBB. If you're, like putting your logical building block, and like if you're putting the parameters that are needed for the logical building block, then you can actually configure your logical building block. And again, like if you're following this, codes, you can configure your photon source in time bin basis. Here we can do the coherent state basis or the single photon basis by setting the alpha variable. Again, like we made the extensive like comments for showing how to operate this code. And then, like by building the LBB, you can actually display what is like your states after passing through this LBB. So by just doing that, like you can do the operations of the LBB, but you can also configure your, your building blocks in more details with like, for example, like conditional amplitude reflection, time bin blocks, which we already write it for you. So then if you do the LBB with like this, the name, again, like, named quantum object can make an operation on the quantum states based on the name to the operation. So after all, like these are pretty high level description. Again, like you need to do LBB, or you need to do the heralding operation for the heralding. You can also get your fidelity and the rate out of like this, heralded density matrix, and like the states to get your fidelity and the rate of the entanglement generation. Then if you run the run, then you will get your fidelity of the space for your protocols. Here we are assuming that like all the parameters are perfect and you don't have any imperfections to get the degradation. And as you can confirm, their rate and the fidelity, their fidelities are given by the 1, depending on the heralding events. Lastly, we can do a little bit more detailed level of like calculation if you're familiar with like all the quantum optical modeling. Here, for example, like we set different parameters. For example, Debye-Waller factor of the quantum emitters, like that's giving the coherent emission. That is the ratio between the coherent emission and the incoherent emission, or quantum efficiency, or like all the functions like for example, like the quality factor of the cavity, or the cavity line width, or the spontaneous emission rate, or the coupling rate that you can define. And then like they will automatically calculate all the cooperativity or like reflection coefficient. We did a extensive work on like how like what is the operation and like what is giving the value. Then it's giving, for example, like this plot. Here, this is a spin-dependent cavity spectrum. If spin is up, by shining the photon into the cavity, we will have this reflection coefficient. If spin is down, then like we will have this reflection coefficient across the frequencies. And if you're setting up our optical frequency here, when the spin is up, like we have a higher reflection coefficient, photon is mostly reflected. And if we are in the spin down states, then it's gonna give almost like 0 reflection. So using this photon to entangle the spins, and like again, like like we configure all the protocols at the at the like higher level with like these given functionals, and running the protocols to get the fidelity. And this time, like we have a non-unity fidelity, because like we are using a imperfect like physical systems like that are not ideal. And like we can also do the weighted average of like different like the heralding cases, which are all shown here. And yeah, like explained in more detail, like in our paper here. So I guess like that is all the part that I prepared for the introduction and the usage of the QRAP. I hope like this helps you and like this is like interesting for your own research and yeah, like before wrapping up the section of the lecture, like is there any questions from the audience? If not, let me pass my let me pass the screen to Prajit. Prajit is gonna talk about the midpoint source protocols, which are a great of interest like these days, and I will be like in the room. So please feel free to give a question, like if you have any like later. Thanks for listening and. Yeah, let me pass it to the president.
So do we want to have a short break for the attendees? Maybe Chuck and Dirk can take questions and I can also help. Yeah.
Dirk suggested like maybe we move forward. So yeah, let's move forward. Thanks, Prajit. But again, like I'm here, so if you have any questions, like please give a question through the Q&A. Thanks.
Okay. So I hope my screen with the website here is shared. So
yeah, looks
thanks
good.
to Dirk and Chuck for the great overview as well as the in-depth dive into the quantum remote entanglement building block simulation techniques using their package. My section of this tutorial is going to talk about this one specific protocol that Chuck mentioned briefly called the midpoint source protocol. Here, I'll take a different approach to how the quantum network simulations is done and talk about how one can use some bespoke analytic modeling mechanisms or, kind of congruently numerical approaches to look into some protocols in depth and understand the different implications of it. So my tutorial will go through the basics of the components that go into the midpoint source protocol, and I'll also talk about how to evaluate the midpoint source protocol. The structure is that I'll first give you a brief intro, talk about the components of the protocol. There'll be some overlaps with what has been discussed already, but I'll just very quickly go through those overlaps just to kind of refresh our memory here. Then I'll focus deep into the entanglement generation sources, specifically how do you get photonic entanglement natively from certain nonlinear photonic processes, and how do you improve that and build a heralded entanglement generation source. I'll do a quick sneak peek into some types of quantum memories and how they're being used, and then I'll give a standalone simulation exercise, which is all embedded in code over here on building and simulating a midpoint source protocol from its components. So all the code here requires only NumPy to run, as well as a file that will be available on the repository called dependencies_midpoint. If you have this, you can open it as Dirk had instructed in either Binder or Colab. If you do that, you should be able to run these codes, or you can separately clone this repository and open it in Visual Studio Code as it works for you. All right, so the midpoint source protocol is one of the two canonical methods to generate entanglement. And I say canonical here because like classical communication where there is no information to send out from the middle that are correlated in some intrinsic way, in quantum communications you have this great resource called entanglement that kind of builds a lot of the basis for all the things that we do in quantum communication. So the midpoint source protocol, as the name suggests, means that I take something that generates entanglement at the midpoint and use the entanglement to be transmitted over channels to two parties at the end. And those two parties receive the entanglement and they process it in some way, or they store it, or they load it, what have you. And then you're able to generate entangled qubits between, or entangled bits between two distant parties over long baselines of messaging. The protocol was first kind of suggested and framed in this name by Jones et al. In this nice paper over here. This is also a good paper or reference to look at if you want to look at the different overarching trade-offs between different protocols. Specifically, the midpoint source protocol will need three main components. Abstractly, you need some form of a quantum memory between Alice and Bob. The two parties need to receive their entanglement and then store them reliably so that they can use them in the future. You need some source of entangled qubits. In this case, since photons are the best kind of qubits to send over long distances, we need a source of entangled photons at the midpoint with some third party who we shall call Charlie. And of course, Charlie has to send these qubits to Alice and Bob. So implicitly, there's a requirement for quantum channels, as well as Alice should be able to classically communicate the information to Alice and Bob. The flow of the protocol is quite straightforward. Charlie will generate a pair of entangled photons, and it's shown by this diagram over here. It sends one entangled qubit to one half of the entangled qubit to Alice, the other to Bob. They also notify Alice and Bob that they have done so. Alice and Bob will then receive the photons and store them in their quantum memories. And then once they have done it and they're sure that they have been able to store their photons successfully, they communicate whether they did so to each other. If Alice and Bob both signal success, then after the time that it takes for light to go between Alice and Bob, or information to flow from one another, they are sure that their memories are entangled. They can use these entangled memories to do any task that they need entanglement for example, teleporting a quantum state, generating a secret key between them, or teleporting a gate. If Alice and Bob, either of them have signaled failure, which means one half of the EBIT is lost, then they will just abort the protocol and try again. The diagram over here is an oversimplification of what goes on, but it captures the high-level concepts that are involved: generation of an entangled pair, transmission, loading, and then reconciliation of the information. It seems that it looks quite straightforward and doesn't require any fancier quantum operations. But however, as with most things in quantum communication, the devil is in the details. We'll look at the different requirements for the protocol to work shortly. So quantum memories are the first things that we mentioned. In general, these are physical systems that are capable of storing quantum information for a long time. In the context of a protocol, we not only require the quantum memories to be able to load the photon and store them, but also be able to tell the end users that, hey, loading has been successful. You may now tell the other party that you were successful. This specifically sets some requirements on what kind of quantum memories can be used, and it is kind of imperative that you have this mechanism for the photons to interact with the memory, be stored, and then the success of storing or not be heralded in certain fashion. So we will refer to this as a heralded photonic quantum memory. You may have seen this in some recent large demonstrations of quantum networks or some other experiments as well. What the memories actually do, we will defer that to a later section. Here are some nice articles for different quantum memories that can achieve this, or a specific subset of these techniques based on interactions with different types of atomic systems or artificial atomic systems. The premier one that's of focus for research at the Center for Quantum Networks is our vacancy center defects in diamonds, specifically silicon vacancy defects and tin vacancy defects. You can also have vacancies in other host materials that can serve as quantum memories, for example, in silicon carbide, and more recently in silicon. You can also have ensemble of atoms that act as memories, although they have some limitations in not being able to be, they don't have that heralding trigger where when you have received your photon and you can successfully say that you have received it. So the next big thing is Charlie, and Charlie needs an entanglement generation source. The entanglement generation source is, of course, something that can generate entangled photons. Generating entanglement can be trivial in certain quantum systems. In certain quantum systems, uh, you know, it's something that you sometimes have to deal with as a bane. You don't want unnecessary entanglement in ways that you can't detect. But generating entangled photons is something that's not possible simply via linear optics in a deterministic fashion. You would have to look into specific nonlinear photonic interactions or nonlinear optical interactions to be able to generate photons that are entangled to one another. Also, the type of entanglement is heavily determined, or the type of entanglement that you generate is heavily determined by what kind of encoding you choose. Some of these encodings have been discussed already, or actually all of the encodings have been discussed already. The most common one is, the presence or absence of a photon, where you describe your logical zero as, or the 0 bar state as no photons or the vacuum, and 1 bar as 1 photon. Then your entanglement generation source is a device that generates entangled photons in the form, vacuum, vacuum, 1, 1, with or without a phase, and vacuum, 1 photon, vacuum, with or without a phase. So these are the 4 bell pairs that we commonly talk about, expressed in this single photon or single rail basis, it's called. In contrast, if we define the qubit in terms of the polarization, or as Chuck just discussed, you can not only have polarization, dual rail encodings, but also time bin, frequency, spatial, or any combination thereof. Then the easiest way to describe the photonic qubits is, 0 bar is presence of a photon in one mode, and 1 bar is a presence of a single photon in another mode. Note that both of these states have 1 photon in comparison to the previous state over here, where there was 0 or 1 photon. Here there's in a net sum of 1 photon in one of 2 modes. It's just which mode the photon occupies determines which state of the qubit you are in. So the entanglement generation source would then generate a state that looks like, both the photons going to Alice and Bob are horizontal or vertical in a superposition, with or without a phase in between them. And one is horizontal, one is vertical, and vice versa, with or without a phase. So these are the 4 bell pairs in the dual rail polarization basis. If we, considered another dual rail basis, for example, the time bin basis, where H can be replaced by the photon being early and V can be replaced by photon being late, or vice versa, you can see how that goes forward. Dual rail encodings are some of the most common ways to encode qubits and photons, because of certain conveniences that we have with respect to doing quantum gates on single qubits. Specifically, from a logical, very basic point of view, any single qubit rotation over here, or single qubit manipulation, meaning if I take a state alpha h plus beta v, changing it to some alpha prime h plus beta prime v, requires only kind of changing which mode the photon occupies or what the relative phase between the 2 modes is. Whereas in this case, if I have to do a single qubit manipulation, I have to add or subtract energy. I have to literally be able to generate or, kind of take away the superposition of 1 photon component over here, which is something that's not going to be achievable simply through linear optics. So the dual rail qubit or dual rail encoding is one of the most, more favorable ways to encode qubits. The final thing that we kind of often take for granted are quantum and classical channels for information transfer. Specifically, a quantum channel is something that's capable of transferring qubit. This is a very non-mathematical and non-rigorous definition, but you can simply think of it as some kind of evolution that the qubit goes through, which need not be unitary. You may lose information or lose some sense of the quantum state when it goes through a quantum channel. And these are, generally used to model all the processes that are involved with sending a qubit from one point to the other. Our quantum channel is going to be very straightforward. We'll look at something known as the bosonic pure loss channel, or sometimes just called a pure loss channel in literature. We also have to consider that there is some classical channels for the parties to communicate information with one another. This is just somebody sending a sequence of bits over some kind of transmission medium to another party. These channels can also have some errors and whatnot, but for the sake of keeping it all simple and only focusing on the quantum part of the network, we will say that the classical channels have very less chance of error or no error at all. With this, we understand all the components that go into our protocol. Let's shift some gears and look at how entanglement can be generated between photons. So photonic entanglement generation must rely on some kind of nonlinear interaction, specifically because you're generating coupled pairs of photons that have some correlations between themselves. Of course, there's ways to do it linear optically, but you have to use single photons, which themselves have to be generated from a nonlinear process in a heralded fashion for a linear optical circuit to generate entanglement out of it. We specifically will consider the case of spontaneous parametric down conversion, abbreviated as SPDC. So spontaneous parametric down conversion, where the process is quite straightforward in terms of how it can be visualized. It's simply a pump photon that goes and interacts with the nonlinear medium in such a way that two photons are created in the signal and idler fields. The signal and idler are just, arbitrary designations of the two generated daughter photons. There is, with regards to quantum communication protocol, the signal idler can be interswitched and it doesn't really matter. What matters is that we have to abide by a few basic physical laws that govern what frequencies the signal and idler photon can occupy. The most important of which is energy conservation. Any pump photon that goes through must generate a signal and idler photon such that the total energy is same. So omega s plus omega I must be equal to omega pump, or rather, the energy of the pump photon must be the same as the energy of the signal and idler photon, and the constant that ties them all together is the reduced Planck constant. Additionally, we need to maintain momentum conservation, where the intrinsic momentum of the photon given by K pump is also reflected in the total momentum of the signal and idler photon. And this is shown by this triangle diagram over here, or can be expressed as K bar of the pump photon is the sum of the K bars, or the K vectors of the signal and idler photon. This is the basic requirement from a high level of what goes on in a nonlinear process. The range of frequencies that can be generated for signal and idler while also maintaining the momentum conservation law is something that is given by the bandwidth of the nonlinear crystal and is generally referred to as the phase matching bandwidth. You can also, a similar process can be done considering a third order nonlinearity. This is a second order nonlinearity. A third order nonlinearity would involve two pump fields and two daughter photon fields, or the signal idler field. The third order nonlinear process is called spontaneous four-wave mixing, but here we will only look at SPDC. So from a single SPDC process, the source of entangled polarization photons, we can only generate a single photon pair. Along with this, we need to be able to, somehow erase the path information of how the photon was created. We can do this by considering two back-to-back SPDC processes, where let's say the first one generates entangled photons from H and V, and the second one generates photons in V and H, meaning the first nonlinear process generates a signal idler photons, although they are entangled to one another in the complete Fock basis. In this terminology, they don't look entangled, but in fact, a single SPDC process not only has the ability to generate a signal and idler, but a more general state that is known as the two-mode squeezed vacuum, which has higher order signal and idler terms. So the first order, however, you have, let's say, H and V from the first nonlinear process. And in the second process, let's say we change it in such a way by rotating the crystal or some other manipulation that the first photon is V and the second is H. Now, if I'm able to erase the path information of which, or the information of which nonlinear process took place, given a single pump photon, the fair assumption would be that it could be either one of them. So the output photonic states exist in a superposition of being in V and H, or H and V simultaneously. This is how you take a single SPDC process and convert it, or build a higher, not a higher dimensional, but a dual rail polarization encoded entangled state, entanglement source generally. Some implementations of this that have been studied in literature, both experimentally and theoretically, are shown in this diagram. The source A shown over here is one of the earliest sources from the group of Paul Kwiat and others. This involves the two separate crystals in orthogonal orientations of their nonlinear coefficients, and they have each have a pair of signal idler beams, but since they are placed so close to one another, the dimensions of the crystal here are greatly exaggerated, but because they will be generated so close to one another, their light cones pretty much intersect, and when you detect them, you cannot tell which nonlinear process was done until you are able to discriminate between the frequency of the polarization of the photon that was generated. The second one over here is something based on a Sagnac loop interferometer from the group of Franco Wong. Another version of the source, which instead of having two crystals involves having a single crystal, but two passes through it. One is the forward pass with beams marked going left to right over here are generated, and the second pass beams going right to left over here are generated, and you can erase the path information by doing something over here. And the fourth one is a summary of all of it in terms of a black box model of how the source looks like. In general, the SPDC process can be understood to comprise of two mode squeezing processes, and the two mode squeezing processes are generating a superposition of states in which the photon numbers are correlated between the two outgoing modes. By erasing the path information internally and with some phase over here, the output state can be written as psi plus or minus with the following expression in the Fock basis. So psi plus or minus is a superposition of over a total number of n photons in a pair of modes with some amplitude factor over here determined by how many photons there are in a single pair of modes. Given that the total given that you have k photons in one mode and n minus k photons in the other mode, and vice versa, given here. So this is the most general model of an SPDC source, SPDC-based polarization entanglement source, and an SPDC-based dual rail entanglement source. And if you write these terms out up to n equal to 2, the P of n is given through the inherent two-mode squeezed vacuum distributions that are involved in writing down the state. The expression is given over here. The math is broken, but you can tell that there is a geometric series. So it's ns to the power n and ns plus 1 to the power n plus 2, where ns is called the mean photon number per mode of the source. We will work in the regime where ns is much, much less than 1. In fact, ns less than 0.2 is where the following description of the state is valid. Namely, if I write the state out in terms of the explicit, in terms of the explicit photon number distributions, for n equal to 0, you only have the 0, 0, 0 terms. For n equal to 1, you can have k equal to 0 or k equal to 1, which gives you this term over here, the 1, 0, 0, 1 plus 0, 1, 1, 0, and this term which corresponds to n equal to 2. The overall thing, since I've truncated kind of in an ad hoc fashion by saying I'm not going to consider anything for n greater than 2, needs to be normalized properly. N naught here is a generic normalization constant. But you can look at the state and already start seeing where you would get polarization entanglement for. Specifically, this term over here, 0, 0, 0, 0, is no photons anywhere. In fact, it's just vacuum coming out. So with the probability of P0, you can say that, okay, this corresponds to the SPDC process failing. If there were no other losses in the system, this is exactly the term that corresponds to the pump photon not getting down converted. Now the second term over here, the one with the P1 over here, if I treat the 1, 0, 0, 1 and or the 1, 0 and 0, 1 as qubit states, this is HV plus VH by square root of 2 with the probability P1. So with the probability P of 1, I am generating the bell pair that I so choose to desire, or so choose to want to get out of the state. But looking at this higher order terms, I don't have terms that fall in the Hilbert space of the qubit as I've defined in the photonic states. 2, 0 and 0, 2 themselves are orthogonal to one another, but they're also orthogonal to 1, 0 and 0, 1 individually. So they are not in the qubit Hilbert space. However, this state standalone fashion, if you had detectors that could tell apart between how many photons you were receiving, you would always be able to tell when a bell pair came out, because you would only ask the question, do I see one photon H and one photon V, or one photon V and one photon H? And if I say anything else, then I reject that outcome and I say I didn't generate a bell pair. But we also have to consider the action of the other components of the quantum network. Most significantly, the biggest thing for a quantum network that limits its performance, and the reason that you have so much research going on into the specific field of how do I enhance the rate of quantum transmission or quantum communication over long distances, is that loss significantly deters our ability to send qubits. For this state, loss does not only reduces our rate, because if I have even loss on one arm with the probability of the photon being lost, I'm not ever going to get a bell pair between them. One half of it will be lost, but also with an equivalent probability, I will have the detrimental term of one of these photons being lost from the 2, 0 or 0, 2 or even the 1, 1 state. And the moment one of these photons are lost, the end users will think, oh, this is probably a qubit, let me declare it as a success. Whereas the photon was lost and you don't really have coherence. So you end up having a state which you think is entangled, but in reality doesn't carry any entanglement in it. For this purpose, P2 is a probability of having noise in the system. And you can already see that if I include a P3 and a P4, all of these terms are going to introduce higher and higher amounts of loss. The way that we get around, or the way that we have to make some concessions to keep our life simple when understanding these systems, is to say that, well, if my distribution is a geometric distribution with a reducing factor every time, I know I have to operate in a regime where I can only have a first order error. If I'm already going to a regime where I have a second order error, if I especially know that nothing beyond P1 is going to contribute to entanglement distribution, I am only going to get a highly erroneous and poor quality entangled state at the very end. So I will limit myself to n equal to 2 and find where this approximation is relevant. So it's for most applications, it's sufficient to consider up to P2, just to kind of make sure that you account for the fact that you can't drive it super hard, meaning you can't put NS super high such that you always have bell pairs coming out of it. The reason that this source is also slightly inconvenient is that this term is generated as a whole every time that a single pump photon goes through it. This is a superposition state. This is not mixed state, meaning this is not like, I'm not saying that this is an ensemble or the generated photonic state coming out of the SPDC-based polarization entangled source is an ensemble of sometimes having a vacuum, sometimes having a bell pair and sometimes having noise. It's a superposition, meaning until I detect the state or make a measurement on it, I'm not sure which of these components I actually truly have projected onto. So this state is not deterministic in terms of generating bell pairs. It is always going to produce the state, but I'm only going to probabilistically detect the bell pair over here that I wish to distribute. The source is hence a bit inconvenient to work for and has high limitations when you want to deploy it on a quantum network. Specifically, you have to operate at very low pump powers, meaning very low mean photon numbers or NS regimes to reduce your higher order noise terms while still keeping your quality of generating the states high. We want to kind of alleviate some of these issues and want to think, okay, how do I go from just having a state where I have to live with the source that is generating the state, but rather think of a smart way to get around some of the problems that this creates. So that will bring us to the next section. I feel free to ask questions in the Q&A. I can see them pop up here, but if there are no questions, these are some resources for understanding some of the fundamental experiments in generating entangled pair generation sources from like some of the most well-known groups in the world that work on this. You'll find more details about SPDC-based entanglement generation sources over here if you want to understand. We also have a tutorial here which uses some, self-defined functions simply from the theory that we have studied on how to understand the different components of the bell pair sources. Specifically, this one shows how if you tune the mean photon number per mode, you have the probability of occurrence of a vacuum, bell pair, and two-pair term in comparison to one another. You can play around with this. This code is, as with other sections of this tutorial, is available over here. This doesn't require any additional packages to run, so you can just copy paste, use NumPy, and you should be good to go with this. I'll leave it to you to test it out. Here, we do something similar, but we just do a ratio of how much is bell pair, how much is a two-pair noise term with the probability that I don't have a photon coming out. All right, so with the ability to, kind of understand what is, or with the ability to understand the stored state generated by the polarization entangled source in the previous section, let's look at how one can then take the step to go towards building a heralded entanglement generation source. Specifically, as we shortly discussed, the noise terms like 2002 and 0220, 1111 are the terms that we want to get rid of. How shall we do this? One very common way that people have tried and have suggested in many forms and iterations is, why don't we just use single photons and some linear optical circuit to generate entanglement? This is, smart because you can detect a single photon from a single SPDC source by just detecting whether the idler mode or the signal mode has a photon. So the undetected mode, up to your detector's noise, whether there's a single photon or not. And then you can build linear optical circuits both on an optical table in your lab or on chip in a scalable, very low loss fashion, so that you can come up with a state that has entanglement to a higher degree. The other instance is to simply take the SPDC source and then have some system which is able to process the photons and then spit them out only if you have the required type of entanglement, specifically the bell pairs there. The system not only like the destructive or the demolition way of doing this is to simply say that, oh, I don't want to send entanglement, I just want to detect it. And that's what you do for most experiments, is to have a detector at the end and you just measure how many photons were seen in what polarization. To have this additional step of the photons being, generated back in a fashion that can be processed by other parts of the network is non-trivial. There's some proposals for it. However, as far as I know, there haven't been any demonstrations of being able to filter out everything but the bell pair from the source. The final idea would be to take the SPDC source and somehow do a post-selection on the source, not by detecting all of its mode, but combining it with another identical source and doing a joint measurement on it. The best idea here is that, okay, I need a bell pair to come out. So if I'm already given by somebody two bell pairs that are, to a very high degree of certainty, good bell pairs, the way that, you generate not a single bell pair from it is to make a joint measurement on two qubits simultaneously from the two separate bell pairs. And the undetected qubits, or the unmeasured qubits rather, are projected onto a bell pair. So this is the famous bell state projection measurement, which is a joint measurement for two qubits that can project them into one of four bell states. The outcomes of the measurement is, I see a raised hand, but I don't know if we can have audio enabled. Could you please put your questions in the Q&A and get to it after the section? So the bell state measurement is the bell state measurement or bell state projection is for the qubits is a very well-defined measurement. You simply do a C0 gate and then you measure the two qubits, and the outcome of your measurement will tell you what state you are projected in. The problem is that or not the problem, but the limitation for linear optical qubits is that the bell state projection cannot be done in a deterministic fashion, meaning that I only succeed half of the time I try to do the measurement. This is because the way that the linear optical circuit is configured, which is equal mixing on two 50-50 beam splitters followed by detectors, is unable to tell apart between two out of the four bell states and only can discriminate between the other halves. So you only get a 50% chance of probability. But if I consider two of the SPDC-based polarization entanglement sources given previously, and I perform this joint measurement in between them, we expect that, okay, if I have a bell pair here, and only if I have a bell pair here, will I get a state S, which if my bell state projection succeeds, S is going to also be in a bell pair. Well, you do not know what state you're putting in. So you said that, all right, I'm going to put the state, I'm going to assume that I have the superposition of all the states that are generated from the SPDC source in their corresponding weights. I then interfere the whole system in a linear optical circuitry, work out the math, and when I get the correct detection patterns corresponding to the successful bell state measurement, there are detection patterns in the detectors, which will tell you which is a successful measurement and which is not. I know that their state S has to have some form of entanglement, and you'll be right. Specifically, if you take the state written previously and you project or do the linear optical bell state measurement on the input modes over here, the outer undetected modes are, projected onto a state which I mark as S over here. And S is a superposition of having a bell pair and another entangled state, which is not a bell pair, but still entangled. It's the superposition of no photons going to Alice and two photons going to Bob, and two photons going to Alice and no photons going to Bob. This is unfortunately, again, not in my dual rail basis. So this part of the state is not usable. And one might conclude that, well, you didn't really solve the problem that you set out to solve. You wanted to get rid of all noise terms. And yeah, that is a correct assertion, but a more astute observation is that if I did not have additional photons being sent to Alice and Bob, let's say through a noisy source or a noisy environment, if I were only sending photons and those photons could only be lost, I'm not adding photons to my channel, this part of the state would never give me an, both of them successfully heralding, aha, I have a qubit without, any additional effects of noise, because you can only lose photons and you cannot gain photons in the modes. The half going to Alice over here is never going to detect a photon. So Alice is always going to say, I failed. Bob may say that, okay, I did or did not detect a photon. And in either case, since Alice declared a failure, you just scratch and restart. And this is the other way around, where Alice gets both the photons and Bob does not. So whenever I do get this component of the state, I can restart. And I don't have to contend with noise limiting how fast I can drive the state. So this state, which we call the cascaded source, was something that we came up with, alleviates some of the issues of the previously established SPDC-based polarization entangled state, meaning that I do get the bell pair half the times, and half of the times I end up with a state which is entangled, but is some form of entanglement that I cannot use, but can be projected away by both the parties saying, both the parties, talking to each other and figuring out if they received a photon. This is nice because the state S is now generated in a heralded fashion, meaning I will know when I have the state S. And when I know that I have the state S, I can, kind of tell both the parties, okay, expect a state which is in this form. It's most likely that you will fail half the time, but with the other half, you'll succeed in generating entanglement if your hardware is perfect at the both ends. Now, this heralding trigger have some discussion on how these terms are useful that I summarized in just discussion here, describing to you what happened there. And there's a tutorial on evaluating the quality of the state and the probability of success of generating the state here, which I'll not go into detail. But because there is a heralding trigger that you can now use to successfully say, aha, I succeeded. So try loading those qubits, or I failed, do not even try to load those qubits. You can now think of, what if I combine 10 of these sources, and even if they succeed, 1/10 of the time, at least one of them would succeed some portion of the time. So I can say that, well, I string up M of them together in such a fashion. I send all the signals of whether they succeeded or not to a controller. The controller then decides which source to send to two ideal quantum memories at both ends that Alice and Bob have. And you can choose, based on the probability of success of each of these sources, whether the quantum memory gets a qubit or not every time slot. If I have sufficiently high number of these, I can pretty much take the probability of success as close to 1 as I want. So if the probability of successfully, triggering each of these sources is P single, meaning that I pump it in such a way that, I'm getting P single probability of generating that state S every attempt, and I have M of them, I want at least one of them to succeed. The probability that at least one of them will succeed, P multi of M, is 1 minus the probability that all of them have failed, which is 1 minus the probability that they succeeded raised to the M, which in the limit of, small p single or large M, you can write as follows. So P multi of M is roughly M times P single. So if I have P single of 1/10, then roughly having 10 sources or more is sufficient for me to, operate the source in a near deterministic or quasi-deterministic fashion. This is the nice part of the source, is that I know when I succeeded, so I can, string multiple of them together and pretty much send one E-bit to Alice and Bob every attempt that I want to send it to them. Of course, on top of this, you would have to contend with network loss and whatnot. But you can see that this is trying to do the best that we can, given the knowledge that Charlie has locally at its point. The way to do this, one way to do this, the very straightforward, numb-headed way to do this is to say that I just build M of these sources separately, and I have some fancy switching circuit, and I'll build as many sources as I require to get to that near to 1 probability of success. But that is going to give us some numbers, and this were calculated as part of the original paper, is something like 10,000 sources would be required for, with some very modest hardware and perfect operational assumptions. This is not practical for any real world implementation if you especially use spatially separate sources. One alternative is to consider that, these are still, separate, individually separated, like physically separate sources, which are on a chip. So you make them really small, and the multiplexing is done on a chip itself. So the whole package is bigger, but you still keep your individual operations smaller. This is possible, but still not the best way to do it. Alternatively, we can consider the use of frequency multiplexing, where I say that, I say that I am generating the state S over multiple frequencies, or I know which frequency I'm generating the state S at. I tell the user to look for that frequency, and I will simply be able to generate the well pairs at different frequencies at different times. So instead of physically separate sources M, I look for the correct detection pattern of the heralding over different frequencies. This was something that we studied in the paper linked over here. My co-author Kevin and I, under the instruction and guidance of Dirk and Saikat, looked at what we call the frequency multiplexed heralded source in context of something we dubbed zero added loss multiplexing. Was proposed in this paper over here. We looked at some really interesting trade-offs of how to operate these sources in such a way that you could, do way better than simply having SPDC sources. The details of the frequency multiplexing are a bit out of scope for this tutorial, but you can look at the original paper for more details. Specifically, you can think of these ARM sources being able to create the state S with a very high probability, with an additional information about the frequency of the output photons. A sister tutorial of the previous one, where we were looking at the cascaded entanglement generation source, is given over here. Maybe I'll take a few seconds to explain what these things are doing. We kind of initialize variables to look at the different parameter trade-offs. Here I will specify some of the hardware parameters that we consider. Specifically, eta A and eta B are what is your coupling efficiency out to Alice and Bob. Eta detector is how efficient your detectors are. Probability of dark click is what is the noise in your detectors, and visibility is what is the about of indistinguishability in the Bell state measurement. We have an inbuilt source function from the dependencies file, which generates the complete density matrix. The elements that are relevant to us are given by the following matrix elements over here. So you can use this to calculate the fidelity, and the norm of, the trace of the matrix will give you the probability of success. And here we plot both of those things over here. And for the multiplex source case, we simply throw in the additional layer of what is the size of the multiplexing, what the different sizes of multiplexing will achieve. So here you have very similar plots to what was in the previous tutorial, but with different sizes of multiplexing, you will see that your probability of success goes higher, whereas sometimes your quality of the state will go lower depending on what parameter regime you choose to operate. A very quick look through what quantum memories are. Quantum memories are, generically systems that can load qubits and store them reliably. For the midpoint source protocol, we can consider two types of quantum memories. One is the absorption-based, or like the reflection-based Duan-Kimball memory that is summarized over here. The memory is able to do a joint C0 gate or a C-phase gate between an incoming photonic qubit and the polarization dual rail basis, with the state of a spin based on cavity or spin-dependent cavity reflection coefficient. Most generally, if I start with the initial joint state of spin in an equal superposition, and the photon in alpha plus beta alpha h plus beta v, or alpha 0 1 beta 1 0. After the interaction through here, you will end up in a state where, depending on which mode the photon occupies, you either have the state with an additional phase or the state being teleported onto the state of the spin. And by measuring the photon, then you collapse your superposition into one of these two things. So once you know which mode you have detected your photon in, either 0 1 or 1 0, you will be able to teleport it with some additional phase correction. Details of this are left, kind of for people to explore on their own. You can take a look at this really nice paper from 2021, where they had worked out the detailed math with respect to the ideal interaction, the interaction with non-idealities, and other detrimental parameters that can go on in realistic systems that implement this. The other way to do this is to say that I will have an indirect loading of the photonic qubit coming to Alice and Bob by simply having the memories emit a photon, and then I do a Bell state measurement at both endpoints. The way that you generate photons that are entangled to the state of the spin is by doing the sequential emission protocol, where you say that you are able to have the memory generate a photon if it's only in spin down state, and no photon if it's in the spin up state, or a photon at a different frequency depending on how your memory is configured. This is for the group 4 vacancies that we are interested for at CQN, where the spin down state will generate a photon and spin up will not generate a photon. So if I'm in a spin down per spin up state and I apply an optical pulse, only half of the state has a photon and the other half has not emitted a photon. And I flip the spin, apply the optical pulse again, then the other half will generate the photon in the next time. And so the spin is entangled with the emission time of the photon. And as Dirk had, as Chuck had shown in his previous tutorial, you can convert between a time bin dual rail encoding to a polarization dual rail encoding using some linear optical circuit. So with all of these components, one can then go ahead and build a midpoint source protocol, and the detailed physical models are, how much you want to consider for your simulation. Here, I will, kind of conclude with showing you a specific tutorial where I have the fully generated analytical density matrix that we are able to generate through some, code in Mathematica, but is not something that we can discuss in the span of this 1 hour. But if I have given you the density matrices, how you can optimize to evaluate the performance of the state. So you can optimize the state generated by the source and the midpoint separately using this function, cascaded source density matrix. This gives you the density matrix of the photons coming from the satellite. And you also have the density matrix of the memories after the swap has been done. And this code goes through how to look at the quality of the midpoint source protocol while trading off between, do I have a better state or do I have a higher rate? You can play around with different parameters. It should be self-explanatory here. And, by tweaking some of these different parameters, you should be able to see, okay, this is going to give me a specific detriment over here. So I would need to, adjust for it by driving it lower or driving it harder and whatnot. This is best, this is an example code that you can kind of use to play yourself. But it gives you a gist of how these protocols are evaluated for, general research that we do. So I think that is the end of my material. Do not see any questions in Q&A. Maybe they've been answered. Happy to take questions now if people have any.
We can also allow to turn on the audio. So like if you have a question, then like might need speaking, then like please raise your hand. Like we will give you ability to turn on the audio.
Any questions?
Seems like we have a content audience, or there's a
There's
Q&A.
a question. Okay.
Jerry has a question. What type of SPDC source are you modeling? I think there are three types of. Good question there, Jerry. So the specific type of single SPDC process is of the three types 0, 1, or 2, and the relation of the polarizations between the photons coming out are determined by the type over there. For the generic dual rail entangled source, you generally consider a pair of type 2 sources, or a pair of type 0 sources, but at orthogonal polarizations to one another. For the specific aspect of quantum network simulation, you don't really have to worry about the exact nature of the polarization of these states. Rather, all you need is that Fogg basis definition of the state, psi plus or minus, given earlier on here. And if it's a dual rail encoded state, anything should be expressible in terms of this state, maybe up to a Pauli operation on one of these terms. So if you had an HH plus VV instead of 1001, you would have 1010 and 0101, and so on and so forth. But all other manipulations should carry forward in a kind of congruent manner.
I'm going to put chat tutor to the test on this question. Let's see. Okay, so chat tutor knows what's going on this page. And I asked this very same question here. So what type of SPDC sources are you modeling? I see that there are three types.
Dirk, audio is a little bit small, so.
Oh, is this better?
Yeah, this is a lot better.
Okay. Yeah, so yeah, what type of SPDC source are you modeling? I see that there are three types, 0, 1, and 2. But they have different characterization polarization characteristics. So Prajit, tell us if you think this is legit, the answer here.
State is correct. Descriptions of the types of SPDC is correct.
So we want to produce this state, right? That's correct. Yeah. Because it knows that, because it's actually looking at the site, so it's able to infer what we're talking about. Okay. State is one of the 4 Bell states, which are maximally entangled states of 2 qubits. Okay, good. There are indeed 3 types of SPDC processes, which are generally characterized by this. Okay.
And it's type 2 SPDC because HV and VH, yeah.
Yeah, HV and VH. Okay, so did chat tutor pass?
Yeah.
Okay. Do we want to ask a follow-up question? Let's see, what is another question here?
I think it's the same question here.
Yeah. There is a question about Bell state symbol, which is wrong.
Yeah, that was my bad.
Yeah.
I think I thought chat tutor size and phis are mixed up, so yeah.
What is the problem?
So
I think
same polarization should be always B, different polarization should be psi. I guess that's typo. Yeah.
Yeah.
Yeah. Okay, any other questions? Good eye there, by the way, anonymous attendee. Let's ask it something difficult. Do you think it can Chuck, do you think that it can synthesize a QREB code?
Yeah, you can try it.
Okay, what did we ask?
I haven't tested it.
Thank you. Thanks, Roberto. What should we ask it? on the QRep. Yeah,
Yeah, I think it's like pretty challenging test.
that's a really tough one, right?
Yeah.
Let's see
And
what it does.
Does it have the, because it needs to have the QRep code here. Is it all here?
No, QR code is in the example notebook.
Sorry, yeah, of course. I need to go there.
Yeah, it's the one below the current
Yeah,
section.
right. You see what it does here.
I think it wants to know what Barrett and Cope is. If we haven't mentioned it anywhere, then
Well, it should know that, right? Let's see.
okay. All right, it knows it.
So far, so good, right? It's getting
Yeah.
it.
What kind
Okay.
of superposition would you need?
How would you like to prepare the initial state of the qubits using QReb?
How about, yeah. Say plus or minus singular states.
That's very polite of it to ask. You don't want to assume what your target bell pair is, right? You should politely ask for it. There you go. Okay, got the singlet. 2 spins, yeah. Can you describe the initial superposition state for each qubit that you would like to prepare? Also, I mean, like 0 plus 1. In the meantime, if there are any other questions, are there any other questions? Please don't hold back. Yeah. I think it's in tutor mode, so it's not answering the question. Spin dependent fluorescence. So okay, so for folks who are still dialed in, what you're seeing is the reason it works quite well is because it's context aware. It knows what you're looking at, and it can synthesize out of the code base that we give it. Now, what kind of building block or operation in the qubit library? Now, Chuck, what is the building block in the qubit library we should use?
I think logical building block library, LBB, or yeah. Let's start from there.
Yeah, so it's in tutor. We have to change the internal thing that it would just answer it. Right now, it's tutoring us, so it doesn't want to just give us the answer.
Yeah.
Okay, how would you like to describe the? How do you want to do that?
I think also we need to provide the full source code in the in the notebook.
Yeah.
The
So
notebook
next time, if people take this course next year, we will have Chat Tutor built out to the point that you can just ask it. You want to do something, it should hopefully write the whole code base. I mean, it should write not the base, but it should apply the code base to the problem.
Yeah, and if people detect issues, report them as issues on GitHub so that the Chat Tutor team knows where the AI
Exactly.
is dreaming.
Yeah, it's an open source. Also, if people are interested in, it's all open source what we shared here with you. So hopefully you will have fun with this code. We've worked a lot on it. hopefully it's a resource for the future. And for folks who are interested in participating to anything, the chat tutor is an open source project. Oops. Yeah, on GitHub. I think I've previously shared that already. Okay, seems like they're letting us off easy otherwise.
Yeah. Final remark, the chat tutor, both chat tutor and the QRep are open source. So if audience, any of like you're interested in, like please let us know or directly
Just participate.
Sorry. Yeah.
Just start coding.